I think we are live. I think we are live. Let's give it a second. Just put it on TikTok just to promote. Let me know if people are up. Let me know if people are up. I want you guys to tell me as well if you want me to do all of module six, or if you want me, oh, wrong one, or if you want me to do, oh, no, it's just not working, is it? There we go. Guys, if anybody's in the chat, let me know if you want me to go through all of module six again, or continue where we went from yesterday. I'll go a bit faster over the stuff that we've already done. OCR A-level chemistry on YouTube, guys. Let me know if you want me to do all of module six. What's up, everyone? Let me know if you want me to do all of module six or just carry on from where we were yesterday. I'll do module six quite quickly. I also have a couple questions to go through once we finish going through the content. Continue, do it all again. I'll leave up the amine naming thing right now because I know a lot of people. I'll just leave it up on the screen. Let me make sure my OBS is working. Okay. I'm leaving up the amines on the screen so you guys can just look at it while we wait for a few people to join. But yeah, all again. Nah, just continue. I'm seeing a bit of both. I'm seeing a bit of both. Mm, unsure. What I might do, I might continue from where we were yesterday. Then I'll do some questions, and then I'll finish kind of going back from where we were. I don't know if that makes sense. I don't know if that's a good idea. All again, all again. 'Cause I might have to speed run all again. I do apologize, but I'll do it. I'll do it quickly. I'll go through it quickly. Gonna go through all of module six. Is 90 enough for an A star? Um, last year I believe it was 92. Okay, I'll do it all again. We're gonna go through all of module six. I'm sorry guys if you wanted me to continue. Just module six. We're not gonna go over. Not gonna be going over module four because it's mainly just what, alkenes, alkanes, alcohols, haloalkanes, that bond M4P. Okay, we're gonna go all again. I do apologize for those who don't want it all again, but it's definitely helpful because I'm just going through the facts, guys. It's everything that you need to be knowing in that exam. As we know, this is just a memory game. Unfortunately, I think it was 92 last year for an A star. Ridiculous. 92 is crazy. So, guys, we're starting now on YouTube. I'm gonna start at 10:05. Yeah, some people are not happy that I'm starting module six again. I apologize. I apologize. But day before the exam, still key information. Maybe I'll remind you of something that you forgot. There's 1, 2 markers, always helpful. And we have a couple questions. In the evening, we're going to be going through 5 NMR questions and 4 unseen mechanisms, which I know are a lot of people don't like those kind of questions. So let's do that. I will do 1 NMR question in the morning. I'm not sure how long we'll go for. As I said, I will be going quickly through the module six content. Uh, There we go. So you guys should memorize organic synthesis map first or go through topics first. I guess one kind of is the other, isn't it? Like as you go through the topics, you are learning the reactions as well. So I don't know. I don't know. Maybe it's kind of up to personal preference, but you are doing the pathways by doing your topic revision. So both sides of P was a pi bonds above and below carbon atoms and delocalized as pi system, whereas delocalized as pi bonds. Yeah. Fred is back. Fred is back, guys. We're gonna be starting. It's 10:05 now. Let's start going through module six. Can you go through how to draw EZ with skeletal formula? I can indeed. At some point. Alright guys, just make sure the stream is good before I start waffling. I don't want it all to be destroyed before I start going. Alright, looks like we're all good. Okay. Alright, starting with module 6, we have Kekulé, and then we have his disproved model with the delocalized models of benzene. What Kekulé suggested? He suggested we had 3 localized pi bonds. Remember, a pi bond is a sideways overlap of p orbitals, and it is alternating double bonds. Then we developed the model with delocalized pi bonds. So we have that pi system, that pi ring, delocalized ring of electrons, and we developed the model like this. The more commonly way of seeing benzene, however, we use this model being drawn even at higher level chemistry, just because it's easier for curly arrow mechanisms. But don't worry about that. What was wrong with Kekulé's benzene, guys? Just making sure. Okay, cool. What was wrong with Kekulé's benzene? We had those carbon-carbon double bonds, but we know that carbon-carbon double bonds are shorter than carbon-carbon bonds. However, this would mean benzene would be deformed. We wouldn't have that regular hexagonal shape. So when the bond length was measured of benzene, we actually saw that every bond was the same length. So it couldn't have been the case of alternating double bonds. The other weird thing about, or the thing that disproved Kekulé's model, was that it didn't react with halogens. If we had the carbon-carbon double bond, just like alkenes with electrophilic addition, need to know that curly arrow mechanism, it would react readily with Br2 or by some halogen, or HBr, for example, hydrogen halide. However, it doesn't because the electron density is too low. It requires a catalyst. As we know, we need the halogen carrier, and it does so by electrophilic substitution. We don't see addition with benzene, we see substitution, electrophilic substitution. And then last, probably the most important thing, the enthalpy change of hydrogenation was less exothermic than expected. Benzene is more stable because we have that electron density spread around because of that delocalized ring of electrons. It's more stable than Kekulé's prediction. So for cyclohexane, if we had that one double bond in cyclohexane, we'd have that enthalpy change of hydrogenation of minus 120 kilojoules per mole. So because we would expect three of these double bonds in Kekulé's model, it would be minus 360 kilojoules per mole. For OCR, guys, you do not need to know the bond length specifically. You don't need to know the bond length, you just need to know that the carbon-carbon double bonds would be shorter than the carbon-carbon single bonds. And that obviously wasn't the case for actual benzene. We had all the bonds the same length. However, so because we would be predicted minus 360 kilojoules per mole, but then in reality it was only minus 208 kilojoules per mole, it was less exothermic than expected. More energy was required to break those bonds, therefore benzene was more stable. So that's the third, so those are the three things, sorry. This proved Kekulé's model and essentially developed our delocalized model of benzene. I hope that makes sense. Then just going over benzene, guys. With benzene, we still have that sideways overlap of p orbitals. So every carbon has that dumbbell-shaped p orbital. Have our 6 carbons, and then we have this pi system ring forming above and below the carbon plane. Okay, so side-on p orbital overlap above and below the carbon plane with that delocalized pi bond ring of electrons, or like pi system, delocalized ring of electrons. All these are accepted in mark schemes. So exactly that, guys, we have the electron density above and below the carbon plane, spread over 6 carbons. That's why we see it so stable. So it has a low electron density. It's unable to polarize molecules. So reactions require catalysts. As we know, electrophilic substitution for benzene, not electrophilic addition. So continuing on, oh yeah, I remember I had to add this thing because I didn't have it in later. For the reduction of nitrobenzene, so if we have nitrobenzene, we reduce it with tin and concentrated HCl, just something you have to remember. We then get our phenylamine and we get 2 waters. To see the amount of this reducing agent that we need, this tin and concentrated HCl, we can simply count the H's. So we go from NO2, we have this NH2, and then because we get rid of both of these oxygens, we're going to need 2 water molecules. Because we need 2 water molecules, so we have the NH2, that's plus 2 hydrogens, and then 2 water molecules, we're going to need 4 hydrogens. That's why we have 6 of our reducing agent. So continuing on, guys, Friedel-Crafts acylation and alkylation. I don't know what my notes are, but it doesn't matter. Okay, so we have for Friedel-Crafts alkylation. For both of these, it's under reflux. For both of these, it's with a halogen carrier. So for Friedel-Crafts alkylation, we have a haloalkane and a halogen carrier, and it's under reflux. So very key thing, make sure your halogens match with your halogen carrier and the haloalkane that you're using. We have our benzene, we add our haloalkane. This haloalkane will become an electrophile. We'll go through that in a second. This is the overall equation. Then we can get this carbon chain onto our benzene, and we have HBr. That's all that we use. We can add these alkyl chains onto our benzene, okay? Or alkyl groups. So forming the electrophile, same idea with most of these forming the electrophile, whether it's halogenation, alkylation, acylation, nitration, it's always the same idea, forming this electrophile in order for our benzene to be susceptible to electrophilic attack, okay? So forming the electrophile, we have our 1, 2, 3, bromine in the second position, 2 bromopropane, with our aluminium tribromide. We form that electrophile, and we form AlBl4-. Remember, our halogen carrier is a catalyst, so it will be reformed by the end of the reaction. So we have our electrophile now, we have our electrophile. Now we can go through the mechanism. The mechanism is the same for every electrophilic substitution reaction for benzene. We're going to have a curly arrow going from that ring, or that pi system, ring of delocalized electrons, to our electrophile, to the positively charged carbon. It's very important. Then on that carbon, on the benzene ring that we're trying to attach to, we then also draw a hydrogen. Then we have heterolytic fission. Heterolytic fission, both electrons and the shared pair of electrons will go to one of the bonded atoms, or in this case, it will go into that delocalized ring of electrons, which was broken in order to attack the electrophile. So it was broken. We essentially reformed that ring with both of these electrons on this carbon-hydrogen bond going back into the ring. So we're left with exactly what we need in this alkylation, and we have our H plus. And then once again, because our halogen carrier was a catalyst, we have to reform it. Not reform, reform, guys. Not reform. So we have our H plus aluminium Br4 minus. We reform that halogen carrier and we get HBr. For OCR, it's just tin and HCl in the reduction of nitrobenzene. Hope that makes sense, guys. So very similar to acylation, we need an acyl chloride and a halogen carrier. Once again, halogen carrier and reflux, okay? So we have our benzene, we have our acyl chloride. R is just an alkyl group. Do not get intimidated when you see R. So we have our FeCl3. Once again, the halogens will match. This can be aluminium or iron, it doesn't matter. Then from here, we get our phenyl ketone, as we can see here, and HCl. HCl, same idea. Let's go through the mechanism and it will all make sense. So we have our acyl chloride and we add our iron trichloride. We form that electrophile. So we just get rid of that chlorine. The CCl bond breaks and then we form iron tetrachloride ion, I guess, FeCl4 minus. So now we have the electrophile that we need for the mechanism. Same mechanism for all of these electrophilic substitutions. We have a curly arrow going from that delocalized pi system, pi ring, whatever you want, to that positively charged carbon on the electrophile that we formed. Same idea, we then have the hydrogen and what we just attached to this carbon on the benzene. We heterolytically, so breaking the covalent bond with both electrons in the shared pair of electrons, going through that now broken positively, I guess positively charged, which is a broken ring of delocalized electrons. And then we form the phenyl ketone that we need and that H plus. Reform the catalyst, guys, reform the catalyst. Is an alkyl halide the same as a haloalkane? Yes, yes it is. As long as you have that alkyl group or carbon chain with a halogen on it, there you have it, haloalkane, alkyl halide. Wait, alkyl halide. Bro, never, yeah, the notes are in my, guys say haloalkane for OCRA is haloalkane, okay? Bro never gave us the notes are in my TikTok bio. This is all, the PDF is in my TikTok bio. Then reforming the catalyst, we have our FeCl4 minus plus H plus goes to FeCl3 plus H. Is it the same mechanism if there's a mono substituted benzene? Yes, and I have a question on that later, which we're going to go through. So exactly the same, reforming the catalyst. Same idea with alkylation. Very similar, guys, just one uses the acyl chloride, one uses the haloalkane. Other than that, it's basically the same thing. Nitration of benzene, less than 55 degrees C for mononitration, otherwise you can get maybe tri substitution, or trinitration in this case. So less than 55 degrees. So for example, we can say 50 degrees, you can say 45, but most people tend to say 50. We perform it in a water bath to make sure we're controlling that temperature. The reaction is exothermic, so we have to be careful. The conditions and the reactants 50 degrees, concentrated nitric acid, and then as we know, to form the electrophile, we need concentrated sulfuric acid catalyst. Overall equation, we have our benzene plus the nitric acid goes to our nitrobenzene and water. Why is there water? Well, we can see we have NO2, so what do we have left? We have H and oxygen left. We also know we're going to remove a hydrogen from our benzene, so we're going to left with one H and an OH, H2O. To form our electrophile, guys, we have our sulfuric acid catalyst reacting with our nitric acid. You can do this all in one step in this overall equation here. I always did it in two when I did my A levels because it just helped me kind of understand it. So from here, our H2SO4 will lose a proton and become negatively charged, and our H2NO3 or our HNO3 will gain a proton to become H2NO3 plus. Now our H2NO3, we're going to want to form that electrophile. So we get with our H2NO3 plus, this decomposes into water and our NO2 plus. NO2 plus being that electrophile that we need for the nitration of benzene. Or you could just write this overall equation of our nitric acid, sulfuric acid catalyst, plus goes to, HSO4 minus, plus water, plus NO2 plus. Mechanism, same thing as always, guys, electrophilic substitution, just gotta know it. Doesn't matter. They may give you something potentially unseen or try to confuse you. If it's electrophilic substitution with a benzene, it's gonna be this mechanism, okay? So now because we have that electrophile, our benzene is susceptible to electrophilic attack. So same thing as before, on the carbon that we're trying to attach that nitro or NO2 to, so to form nitrobenzene, we get heterolytic fission. I'm going to keep saying it, guys, heterolytic fission, breaking the covalent bond with both electrons in the shared pair going to one of the bonded atoms. But in this case, they're going to reform that broken positive ring. And then we have our nitrobenzene plus H plus. What do we know, guys? We need to reform our catalyst. Reform our catalyst. I think the overall is probably just easier just to know, but I always did it two steps, so I'm a bit biased. No, you do not need to do two steps. You can just do one step. So you will not lose any marks if you don't do it in the two. Reform the catalyst, guys. What was our catalyst? We had that sulfuric acid catalyst. Make sure sulfuric acid catalyst. Okay. So we know we have a H plus left over. Perfect. We have our HSO4 minus plus a proton goes back to reform that sulfuric acid catalyst. So continuing on, guys. I believe it's phenol. Never mind. More reactions of benzene. Same thing. We're forming the electrophile. This is all the same electrophilic substitution. The halogenation can be any halogen. Make sure your halogen matches to your halogen carrier. So we have our benzene plus our halogen, AlCl3, or iron trichloride. It can be iron or aluminium. Then we get that chlorobenzene and HCl. HCl, because we lose that proton, we're going to go through it. Electrophile, we have our halogen carrier plus the halogen. We're going to form the electrophile that we need. In this case, it's Cl plus, could be Br plus, it could be I plus, whatever. Then we have our AlCl4 minus. So homolytic is only for free radical and everything else is heterolytic. You may also see homolytic potentially in some unseen mechanism. They may try to use your knowledge of the free radical substitution. Everything else tends to be heterolytic. Yes, I can't think of anything else homolytic right now. So the H plus and the SO4, what if they ask for a reason? Is it because each atom gets an electron? The reason for homolytic fission is because we need those highly reactive free radicals, if that's what you're asking, with that unpaired electron. Is this a recap? This is a recap. We're going to be continuing with the module 6 and we have some questions. So same idea with the electrophilic substitution mechanism. I'm repeating myself, but you guys got to know this off by heart because they will ask one of these mechanisms very likely, or at least part of it in some longer question. Benzene with our electrophile Cl plus, same idea. To that benzene to the carbon on the benzene that we're trying to attach that chlorine to. We have heterolytic fission. Am I going to say it again? I'm going to say it again. The breaking to a bond where both electrons and the shared pair of electrons go to one of the bonded atoms. We do use this in many, many mechanisms, so it's key just to know that definition. They may ask it as well. We reform that broken positively charged ring, horseshoe ring. Remember that horseshoe ring needs to be pointing to the carbon that we're trying to attach to. I think it needs to cover at least four of the other carbons, but ideally it would cover all other five. Okay, I think that's what they say in the mark scheme. Form the chlorobenzene and the H plus. Reform the catalyst. We have the halogen carrier, halogenation, acyl chloride, alkylation and acylation. And for this halogenation, we all need halogen carriers. Match your halogens up, guys. So we have our H plus AlCO4 minus goes to aluminium trichloride, reform the catalyst, and HCl. We can see that works out with our overall equation. So the directing effects, guys, are very important. Good way to remember it. So let's just go with the electron donating groups first, and I'll tell you the good way to remember it. So electron donating groups will be our OH and our NH2. What happens? The electrons partially delocalize into that ring of electrons, increasing the electron density at carbon 2, 4, and 6 when we have OH and NH2. So we're increasing the electron density of our delocalized ring of electrons, or the pi system. Therefore, it will be more susceptible to electrophilic attack. So in this case, with OH and NH2, they increase the electron density at carbon 2, 4, and 6. These are more likely to react. Then we have the electron withdrawing group, NO2. The way to think of it, NO2, no. Yeah, no, so we're not donating, we're going to be withdrawing. Okay, that's kind of the way I remembered it. I know a lot of other people also remembered it like that, so if that helps you, then it helps you. So we have no electron delocalization. It withdraws density from the pi system, making the carbons essentially the opposite, making carbons 3 and 5 more likely to react. So for example, with our nitrobenzene, we know that NO2 is electron withdrawing. Is electron withdrawing, so if we add chlorine, then we have our halogen carrier. As we know for halogenation, carbon 3 and 5 are more likely to react. So then we'll have that chlorine attacking either carbon 3. I guess it would be carbon 3 if it's mono substitution, either way. Or we could have 3 and 5 if we have two chlorines, or 2Cl2, and then we have HCl. If we have phenol, and we react it with a halogen, we know the phenol, electron donating group, carbon 2, 4, and 6 increase in electron density, making them more likely to react. So we have that chlorine at carbon 2 plus the HCl, or it can be 4. key thing I want to say with the nitration of phenol, because we have that increase in electron density in the ring because of the electron donating group, as the oxygen partially delocalizes its electrons into that ring. If we have it with dilute acid, we get mono substitution, which is nitro, I guess nitrophenol, 2-nitrophenol. That could be, sorry if that's wrong, guys. I believe that's 2 plus H2O. Then we have concentrated nitric acid. If we had concentrated nitric acid, we're going to get a tri-substitution. So we have our phenol plus 3HNO3, that nitric acid that we need for the nitration of benzene. We're going to get a substitution at carbon 2, 4, and 6. And then we have 3H2O. Now looking at phenol, guys, actually, I will ask you guys a question just to get a little bit of interaction. Yeah. I kind of already showed it anyway. The uses are antiseptic, dyes, and detergents. There's a good chance they'll ask you a use of phenol. You have to know one of these. And most people just say antiseptics, but dyes and detergents are also fine. Why is phenol more reactive than benzene? We already established that the OH group is an electron donating group. Its electrons will partially, or a lone pair of electrons will partially delocalize into that pi system, pi ring, delocalized ring of electrons, whatever you want to say. So lone pair on the oxygen, sorry, partially delocalizes into the pi ring. Just going to make sure the stream hasn't crashed and my laptop is getting hot. Looks like we're all good. So the electron density increases in the ring, making it more susceptible to electrophilic attack, or you can say more polarizing. Both are fine. Remember, in order to get electrophilic substitution, we are inducing dipoles, making those molecules polar. Okay. Phenol is a weak acid. This is very, very important, guys. I keep on showing it anyway. Guys, how do we differentiate between phenol and a carboxylic acid? If you already saw, I apologize. How do we differentiate between phenol and a carboxylic acid? Let me know, let me know. I will be honest, guys. I'm seeing a lot of people saying chromatography won't come up. I have a feeling that we're going to see a little bit of gas in chromatography. Potentially something asking what affects retention times, something like that. We will get onto that in a minute. But let me know how we can differentiate carboxylic acid and benzene, exactly sodium carbonate. Because phenol is a weak acid, it will not react with a weak base. However, our carboxylic acid will react with that weak base. And we will see effervescence because CO2 will be produced. Because if we have acid plus metal carbonate, we're going to have that carbon dioxide, H2O, and our salt. Sodium carbonate, sodium carbonate. Perfect, perfect, perfect. So phenol is a weak acid. It does react with strong bases like sodium hydroxide and metals. However, it's too weak to react with weak bases like sodium carbonate. So we have our phenol, add sodium hydroxide. We do get that sodium phenoxide. So we have that O minus and that Na plus because it will react with that strong base and we form H2O. Why do we form H2O? Well, we lose this hydrogen. We still have this hydroxide ion remaining. H plus a hydroxide ion is going to give us H2O. Sometimes you just have to look at what you lose in order to figure out the products. I will say, in doubt, H2O tends, if they give you some reaction, you're unsure what one of the products are, H2O tends to be a little bit of a good gamble. Unless it's an acyl chloride, then it tends to be HCl, that white steamy gas that we do normally have to use a fume cupboard to make sure we're not breathing in that toxic gas. So exactly that, guys. We can use this fact. Exactly, exactly. Perfect, guys. We can use this fact to distinguish phenol from a carboxylic acid. Carboxylic acids do react with that sodium carbonate with our products of H2O, CO2, and a salt. We see effervescence. They might ask for the visible change. You say we see effervescence or bubbles if you really want. Say effervescence, sorry. The next thing, key thing to know, like with our nitric acid before, phenol does react readily with halogens. So we will get that tri-substitution. So we have our phenol plus 3Br2. We need no halogen carrier because it reacts readily at room temperature and forming a white precipitate. Forms a white precipitate, guys. Key thing to remember. So phenol plus 3Br2, we get that tri-substitution and we get 3HBr. Why do we get 3HBr? Because for each time we have these substitutions, we lose the current hydrogen attached to carbon 2, 4, and 6. And we also have 1Br left for each of these bromine molecules. We are also doing one NMR question at the very end of this session. Let's just see how much we can do, guys. Let's just see how much we can do. Moving on to acyl chlorides, we did all of this yesterday. So we're going to go relatively quickly. So this is an example of propanol chloride. This is what we're going to be using as I go through all these examples. Why is it propanol chloride? Well, we have our acyl chloride functional group, that carbon double bonded to an oxygen and then single bonded to a chlorine. Propanol chloride. Then from here, what's our longest carbon chain? 1, 2, 3. Propanoyl chloride. Propan-noyl chloride. So you have to know how to name it. Acyl chloride to a carboxylic acid. Tell me, guys, before I show it, tell me, if we want to go for an acyl chloride to a carboxylic acid, what do we have to do? And then what do we have to do for carboxylic acid to an acyl chloride? Let me know, guys, let me know. Why is it tri-substituted? It's tri-substituted because it reacts readily with bromine. So it's going to keep on reacting and do every substitution that we can because it reacts readily with bromine at room temperature. You would not get a mono substitution. It would be a tri-substitution forming that white precipitate. H2O. It's perfect, guys. And what if we wanted to get from a carboxylic acid? I'm seeing both ways. I'm seeing both ways. So if we want to go acyl chloride to a carboxylic acid, we are going to need water. Perfect, guys. Exactly, SOCl2 for the reverse. Amazing. So we have that acyl chloride, the propyl chloride. Add water. What do we get? You can kind of just once again see what's involved. We're going to get rid of this chlorine. We know that. We're forming a carboxylic acid. So we're going to have an OH from here joining on. So we're going to have that 1, 2, 3 propanoic acid plus HCl because we get left with a hydrogen from our H2O and we lose this chlorine. HCl, be careful, guys. Commonly in acyl chloride reactions, we do get that white steamy gas and we have to use that fume cupboard because it's toxic. It's a very key thing to know in these kind of questions. Obviously, the question will normally specify whether it's aqueous or gaseous, but if they ask a problem or why you have to use a fume cupboard, we do tend to say HCl is indeed a white, steamy, toxic gas. So here, carboxylic acid to acyl chloride, we'll use our propanoic acid plus SOCl2. I saw all of you guys saying that. SOCl2 to make it, and then add water to make back. Yes, perfect. So adding that SOCl2, we get our acyl chloride. When trying to find the products, as we know with acyl chlorides, one product tends to be HCl, and then we get SO2. Why do we get SO2? With these, when we're trying to build these reaction equations, just see what we have left. We lose this OH, and one of the Cl's goes to it. So what do we have? We have an OH, and we have an SOCl. So that will make sense to form HCl, and then we're just left with SO2. Do we make HCl for all acyl chloride reactions? Not all acyl chloride reactions, not all, but the vast majority, yes. The vast majority, yes. It's a common thing to remember, especially if you're stuck. For me, there's no link. There should be a link of the PDF. Guys, we will be doing NMR in the evening, and there are some arene or benzene questions, so that will be useful. Acyl chloride to a primary amide, we need ammonia, guys. We actually need 2 ammonia molecules. Why? Because we know we're going to have that amine here. So we have the amide, sorry, that carbon bonded to the nitrogen, double bonded to the oxygen, and we add 2 ammonia molecules. Why? Because one of our products is that ammonium chloride or ammonium salt. It will be ammonium chloride because we have that Cl and we have that NH4+. Because we have 6 hydrogens, we lose 2 to form that, in this case, primary amide. Why is it primary? Because this nitrogen is only bonded to 1 carbon. Why isn't there an acyl bromide? Guys, smash the like if you want there to be a acyl bromide. And subscribe. Okay, anyway. So acyl chloride, primary amide. We just need ammonia. And these are your products. You have that ammonium chloride and you have that primary amide. If we want a secondary amide, same idea, but instead of ammonia, we're going to use a primary amine. Essentially just adding 1 more carbon attached to that nitrogen. So we have our acyl chloride. Then we have that primary amine. In this case, I chose ethylamine. Nothing crazy. And then remember, guys, to name our amines, the shorter carbon chain. Well, in this, okay, to name amides, we don't have to worry about this. I will go on to naming amines in a second. So naming amides, the thing that's attached to our nitrogen, we're going to count the carbons. 1, 2. That's going to be ether. So it's N-ether. The same thing with an ester, but we have like propyl, ethanoate, or ethyl, propanoate, whatever it is. The thing that's bonded to the nitrogen, we'll take that alkyl name, okay? So we do N, ethyl, because there are 2 carbons, and then how many carbons are attached to this double bonded oxygen on this side, on the left side? 1, 2, 3, propanamide, or propanamide, however you want to say it. Product, once again, what do we lose? Same idea with forming esters, guys. As with a carboxylic acid, we would lose the OH here. In this case, we just use a chlorine. And then we know, like with our alcohol, we would lose a single hydrogen, same idea. We lose a single hydrogen on this amine. So we lose a hydrogen, we lose a chlorine, so we get HCl. Nothing crazy, nothing crazy. Hope that makes sense. Anything can come an unseen mechanism. Unseen mechanisms tend to use knowledge from your known mechanisms, okay? So esters, guys, very similar to naming our amides. This carbon chain that's attached to the single oxygen, or the oxygen that's single bonded to the carbon, this will be our alkyl chain. So 1, 2, 3, going to be propyl, sorry. Then 1, 2. We have two carbons on the side that's double bonded to the oxygen, so we're going to have propyl, ethanoate. Nothing scary, nothing scary. Synthesizing esters, we can get a carboxylic acid plus an alcohol. What do we need, guys? What do we need with a carboxylic acid and an alcohol? It's not just a carboxylic and an alcohol. Like you guys can already see, we need heat, but what else do we need? What else do we need? I hope the naming thing was helpful. Let me know if you guys want me to go over the amide naming or the ester naming as well. I'm just gonna wait till I see the chat. It is a bit delayed for me. Live on YouTube, guys. Live on YouTube. You can't see my screen. We're on YouTube. We're on YouTube. Concentrated sulfuric acid. Perfect. Acid catalyst, sulfuric acid, carboxylic acid, concentrated acid 4, concentrated acid 4. Yes. There is another way. Guys, before I get there, type in the chat what is the other way to go from an alcohol to an ester? And tell me the products if you can as well. But I'm going to go through this because the chat is delayed, so type it in now. And then I'm going to go through this as we do that. So, the carboxylic acid and an alcohol. So, we're forming propyl ethanoate. What do we need? Well, we're going to need 1, 2, 3, propanol or propan 1-ol plus 1, 2. This is ethanoic acid. We take heat and concentrated sulfuric acid. We get our propyl ethanoate. What do we lose? We lose that OH from the acid. We lose one hydrogen from our propanol. We get our propyl ethanoate. What are we left with an OH and a hydrogen? We get H2O. Nothing scary. Let's see here. Acid anhydride and an alcohol forming an ester and a carboxylic acid. Perfect, perfect. It looks like everyone is all good with that. Acid anhydrides. Oh my god. Okay, here we go. So acid anhydrides, this is also the naming explanation as well. So we have our carbons, each double bonded to an oxygen with that single oxygen in the middle. There is no need for a catalyst with an acid anhydride plus an alcohol. So with our acid anhydride, this is ethanoic anhydride. Why? Because we have two carbons in each half. Okay? If we had two carbons on the left and three carbons on the right, it would then be ethanoic, propanoic anhydride. So don't get intimidated if there are different lengths of chain, and normally they would ask you for a certain product if you're using an acid anhydride, so you can kind of work from there. We add our alcohol, not sure why I did it displayed, but here we are. We have propan 1-ol. So we form, you can break one of these two bonds, it doesn't matter which, you'll get the same two products. So you get, indeed, with our CH3 bonded to the oxygen, we lose essentially the rest of our carboxylic acid, and because we know we lose that hydrogen from the alcohol, that hydrogen will go, so if we were to break this bond here, that hydrogen would go to this oxygen to form that carboxylic acid, and the rest of the molecule would form that ester bond with the carbon because we lost the hydrogen. So carbon single bonded to this oxygen and the rest. So we get left with that propyl ethanoate and we get the carboxylic acid. Which one would you say first? With ethanoic and propanoic, alphabetical order. So we say ethanoic, propanoic. So continuing on, guys, acyl chloride plus an alcohol, no need for a catalyst. We're still forming an ester, acyl chloride plus an alcohol. Same idea as before. We lose, instead of that OH on the carboxylic acid, we lose that chlorine. So we have, what is this? 1, 2, ethanoyl chloride. 1, 2, 3, we have propanol, propan 1-ol, we keep saying it. And then we know we lose one hydrogen from our alcohol and we lose that chlorine. We lose a hydrogen and a chlorine. We're going to form that ester, forming that ester bond between that oxygen and that carbon double bonded to the oxygen plus the HCl. No catalyst required. No catalyst needed for the acid anhydride plus alcohol or the acyl chloride plus alcohol. However, we do need concentrated sulfuric acid for carboxylic acid plus an alcohol. Oh yeah. Okay, I was gonna ask you guys to do this. I think this happened yesterday as well. I already showed it. So just going through one, two, three, propel because it's on that carbon single bonded to the oxygen. 8 p.m. will be five NMR questions, and then I will do one at the end of this one potentially. We'll just see how long this takes. I'm trying to get through this as we can, but I know this is helpful. Just getting all that information at once. I think I did something similar before my exam, just going through the whole thing. Which one will react with alcohol? It's ethanoic, propanoic, and hydride. It depends what your product will be. Normally, they will give you. First of all, they haven't really given this often in exams, but if they want a desired ester, then um then they'll tell you because this is kind of like not commonly known things. What you can do is they'll normally give you the desired ester, and then from there you'll figure out which bond to break. There's nothing in the course story which tells you which one you need to know. Maybe in AQA they tell you, but if OCRA they normally give you a desired product because one may be major, one may be minor, but you're trying to get to a certain thing normally in these kind of questions. And then with this methyl butanoate, just count the carbons. This is going to be our first carbon because it's double bonded to the oxygen. Yeah, exactly. First carbon because it's double bonded to the oxygen. So you have one, two, three, four. So that's your butanoate. But it's two because this carbon will be the second carbon and we have that methyl group attached. So we have propyl, two, methyl, butanoate because the longest carbon chain is four. So continuing on, guys. I'm not sure. I feel like we're getting there. Yeah, we're getting there. So naming amines, bit of phenol and acyl chloride reactions. So if we have phenol and acyl chloride, remember, phenol is a weak acid. So if we react phenol with a carboxylic acid, this is going to be a very, very slow reaction because it's a weak acid plus another weak acid, really, carboxylic acid. So it's a very, very slow reaction. There would be a reaction, it would just be very slow. So with phenol, we react with an acyl chloride to form that ester bond. Once again, lose the H from the phenol, lose the Cl from the acid. We form HCl as a byproduct. Remember, toxic, guys, toxic, toxic, toxic. Yes, we always name the alkyl group first. Okay. I don't know how long this live stream will be, guys. I don't know. We're just gonna keep going through all this and I have a few questions. So we'll just see how long it takes. Maybe an hour and a half, maybe two. So 10 till 11:30 or 10 till 12. So this is our phenyl ethanoate that we form. Why is it phenyl ethanoate? Well, because bonded to this single oxygen, it's our phenol essentially, or phenyl, sorry, because we have that benzene group. So that's phenyl, because that's what's bonded to the oxygen. So that comes first. Ethanoate, one, two, ethanoate. Yeah. Because we have two carbons in that longest chain bonded, sorry, double on that side that's double bonded to the oxygen, and we form HCl as another product. Naming our amines, guys. I know you guys like naming amines. They're not scary, but I feel like it's not taught very well in a lot of schools. So let's just go through it. For primary amines, really similar to other things, guys. Longest carbon chain, one. I don't have an extra chain. There's no extra chain here, is there? No. Okay. So naming amines, we have that primary amines. Okay, so what longest chain? One, two, three, four. It's gonna be butan. Where is that? Well, there's only one group here. It's that amine functional group on the first carbon. So you have butan, one amine. Why do I have an extra chain in the Cl? Um, so I'm not really 100% sure what you mean. Am I looking at the wrong thing? I'm not sure. Let me know if I'm making an obvious mistake. So anyway, amine on that first carbon, we have that butan 1 amine. If it was on the second carbon on our longest chain, it's the only group here, it'll be butan 2 amine. Do not get intimidated by naming amines, guys. For primary amines, they're even easier. So then, for our secondary and tertiary amines, the shorter chain, guys, the shorter chain will be N-alkyl. The rest of it is the same as your primary amine naming. So here, let's look at this. How many carbons are bonded? One, two. Secondary amine. The shorter chain will be on the left here. We just have a methyl group essentially. So we're going to have N-methyl because it's a shorter chain. Then looking at the right here, we have one, two, three, propan, whereas that amine group is on that first carbon of one, two, three. So it's going to be propan, one amine. So we're going to have N-alkyl for the shorter chain. Okay, so we have N-alkyl for the short chain, and then going on to And then going on to our tertiary amine. Why is it tertiary? Because our nitrogen is bonded to three carbons, carbon, carbon, carbon. The shorter chains are our two methyl groups. So we have NN, dimethyl. Why di? Because there's two of them. Then we have, looking at that longer carbon chain, 1, 2. We have two carbons. So we have dimethyl, ethan, one amine. Same as that primary amine naming when we look at that longer chain. When we look at the shorter chain, we have to add in those ends. Then if we have a diamine, guys, just like if we had dichloro, dibromo, whatever, it will be at the suffix, sorry, because it is, we never use the suffix. So we have longest carbon chain, 1, 2, 3, 4. Butane. You get the ane back for some reason here. I was never sure. I was never completely understood by this. I think it's because we have that N, like literally English, guys, where we have that vowel with the consonant, whereas here we have the consonant with the vowel. So I think that's the only reason why you get that E back. But this is just something to know when we have that die, in this case, or try. So here we have 1, 2, first position, third position, butane. So we're going to have butan or butana, 1, 2, diamine. Why is it one amine? It's one amine because on this carbon chain, our amine will be the highest priority functional group. So this will be the first carbon. I don't think you would even need to say one amine. You're right, yeah, because it could only be there. It couldn't be two because unless you have some other higher priority functional group on the other one, then it wouldn't even be, yeah, then it would be amino or something else. So yeah, in this case you wouldn't need the one, but yeah, because it's that higher priority group, it's the only group it would be on that first carbon. So a bit of Tollens reagent. Ah, I meant to ask you guys. Oh well, Tollens reagent. We form that silver mirror. It uses aldehyde can be oxidized further to a carboxylic acid, reducing our silver ions, whereas our ketone cannot be further oxidized. So Tollens reagent, test for an aldehyde. It contains silver ions. We know it forms that silver mirror in the presence of an aldehyde. We have this AgNH32 or positive ion in the aqueous solution. It's colorless and it's made by silver nitrate, sodium hydroxide, and ammonia. We use the fact that aldehydes can easily be oxidized, whereas a ketone can't. The aldehyde oxidizes to form the carboxylic acid. As the aldehyde oxidizes, that silver mirror forms because our positive silver ions are reduced to solid silver. So we form that metallic silver. Good thing to know, you need to know it. Chiral centers, guys, what is a chiral carbon? Tell me what a chiral carbon is. Tell me what a chiral carbon is. As I wait, because it's very, very slow for me. We know that in these exams they tend to give you very, very large molecules in the multiple choice, and they'll ask you how many chiral carbons are there, and you have to be very, very careful with symmetry when looking at these questions. We've seen it come up many, many years. I feel like out of 2022, 2023, 17, 19, 18, I think we saw it potentially like maybe every year. Maybe only there was 1 or 2 years where it didn't come up. Hmm. Exactly that. It's a carbon bonded to four different atoms or groups. As I said, check for symmetry to see if it's a cyclic molecule. Make sure it's the same all the way around if you're saying that it's not a chiral carbon. If it's different on the way around, likely thing will be it's a chiral carbon. So the Tollens reagent, is it still 2O? It would not be 2 because you only go one step of that oxidizing. Because you're oxidizing an aldehyde to a carboxylic acid. So we know if we go alcohol to a carboxylic acid, we go one and we go two steps. Aldehyde, carboxylic acid. We still form one water because we're only forming water when there's an alcohol involved. So that aldehyde to a carboxylic acid will not form any water, only when we have that alcohol involved. So if we go alcohol to an aldehyde, we have water. If we go alcohol to a ketone, we have water. Okay, but not from an aldehyde to a carboxylic acid. So from here, guys, when we have that chiral carbon, we get two non-superimposable mirror images. I wanted to show what I meant by the symmetry. So if we have this lovely organic molecule here, we can see that we have two chiral carbons. Why? Let's look at each carbon. This carbon, hydrogen, which we don't see because it's skeletal, the methyl group, then going all the way around, we can see this carbon is 1, 2, 3, wait, sorry, 1, 2, 3, 4 away from the chlorine, whereas this one is only 1, 2 away from the chlorine. Not symmetrical, different groups on each side. Same thing with here. We have a chiral carbon because we're bonded to a hydrogen and a chlorine, but then going around, this one is two away from that methyl group, whereas on this side we have four away from the methyl group. However, here we have a symmetrical molecule, so organic molecule. So if we have this chiral carbon here going around, each carbon is 1, 2, 3, 1, 2, 3 away from the chlorine, and 1, 2, 3, 1, 2, 3 away from the methyl group. So because it has the same group attached to it, due to the symmetry, these are not chiral carbons. They will not show optical isomerism, however you want to say it. Who is Serge? I'm not even sure who Serge is. How was the top one chiral? How was this one chiral? Because we have a lack of symmetry. We have this carbon is bonded to a hydrogen, a methyl group, and then going around, we have different lengths going to that chlorine, or like different distances away from the chlorine, therefore it's chiral. Whereas this one would not be chiral. So what are the problems with producing chiral drugs? Separation is expensive of those isomers. They can have side effects. What is the solution? The solution is to use a chiral catalyst and chiral synthesis. These are two solutions. So we're only getting that desired isomer that we want from the organic molecule, which has a certain chiral carbon. It's very common in pharmaceuticals for them to have to do this, but it is expensive. That's why we're going to use a chiral catalyst. So what's an example, a horribly drawn example, might I say, of two non-superimposable mirror images. So here, like chiral carbon. Why chiral carbon? Why is it chiral? For different atoms or groups. So in this case, it will be groups. We have that bromine. We have a hydrogen bonded to it. We have a methyl group, and we have this ethene. So because we have four different groups, we can draw. We know it's going to be that tetrahedral shape. Two of them will be on the same plane. It's always going to be the same tetrahedral shape with these chiral carbons. Then we have the wedge, one going out the paper, one going into the paper. So we have the wedge and the dashed line. These kind of go in the similar direction. You guys know how to draw tetrahedral. Have the mirror images, so just draw the mirror image in with that dashed line. Yes, you can use enzymes. That's a good point. You can also use enzymes to get your desired chiral drug normally. I have seen that in OCRA, but normally you don't have to say it'll ask one or two things and this is enough information. But yeah, you can actually use enzymes. It's a good point. I do remember one of my friends who was doing medicine was saying you can actually use enzymes. He was telling me that before the exam, so yes, you can definitely do that. Does it matter which one is the wedge or the dotted as long as the isomers are mirror images? I believe it does not matter. I believe it does not matter. You can check that. You can check that in the textbook if I'm chatting, but I'm pretty sure it's fine. Okay, polyamides and polyesters. I believe this is what we got to yesterday. 50 minutes in. I apologize for those who wanted me to continue. So polyamides, these are condensation polymers. We know with alkenes we have addition polymerization. Here we have condensation polymers. Why? Because we're removing H2O. As we know, remove if it was a carboxylic acid and an alcohol, remove the OH from the carboxylic acid and the hydrogen from the alcohol, forming water. So that's your condensation polymers. So how can we form these? We can have dicarboxylic acids and diamines, for example. So we would have N-diamines and we'd have N dicarboxylic acids from here. Guys, this nitrogen should have a hydrogen on it. It should have a hydrogen. We lose one hydrogen, not two. I'm going to keep saying it in case someone's watching the recording. Both of these nitrogens should have a hydrogen onto them, okay? We lose one hydrogen, not two. One hydrogen. Same as the alcohol. We lose one, all right? Anyway, so we form this amide bond, that N bonded to a carbon, which is double bonded to an oxygen. And then we extend out those bonds, in the brackets, add a little n. Just know what it looks like, know how to form it. Yeah, we're doing one NMR today, and we're doing loads of NMR tonight. How many waters do we form? We form 2n minus 1. Why is it minus 1 waters? Because we're going to have one amine group and one carboxylic acid group at the end. So those two would have formed together to form one water. So it's going to be minus 1 water. Because we're not forming the amide bond with those two. So amino acids, guys, this is a single amino acid. If we have n amino acids, so this one's right, guys. We do have that hydrogen for on nitrogen. This is correct. This one is not correct. I'm gonna keep saying it just for the recording. Okay, so we have n times our amino acids. Same idea. We form amide bonds on each end. So we just get rid of a hydrogen, get rid of the OH on the carboxylic acid side on that functional group. and then we extend out the bonds. Because we remove the OH from our carboxylic acid and we remove a H from this amine, we get H2Os. Why is it N minus 1? Because we have an amine on left on one side, carboxylic acid on one side. Remember, because we have that carboxylic acid group and the amine group on our amino acids, we don't need two molecules, it's just one molecule. So we have N of these, and then we're going to form one less water because we're forming one less amide bond because of the N's. So we have N minus 1 molecules of water. So we have a diamine and a diacyl chloride. Another way we can do it. This is very, very similar, guys, to a diamine and a dicarboxylic acid. Same thing. But instead of losing that OH from the carboxylic acids, we're going to be losing, that Cl from your diacyl chloride. So same idea. Okay, this time we do have our hydrogens. This is perfect. We lose one hydrogen from each side, forming the amide bond. We lose those chlorines the same way we lose the OH on carboxylic acid. What do we form? We're going to form HCl for each one. So we have N monomers here, N monomers here. So we're going to form N of these polymers. However, it's 2N minus 1. Why? Because we have that one amine group at the end and one acyl chloride group at the end. So we're forming one less water than each of these water molecules. Because for each of these, we're going to be forming water molecule here, and so on, so on, so on. Just checking the chat for just a second. Why are the grade boundaries so high? Because because organic chemistry is a memory game and loads of people, especially Oxbridge, Imperial candidates, will just be doing this, especially even for their interviews, and it's just a memory game. They like to put really high grade boundaries just because people get a lot right. So a lot of it's just filling in flow diagrams. So you have to be confident with it. So continuing on, guys, I believe we have ketones or polyesters. We have polyesters. Same idea. So this time we have diols and dicarboxylic acid because it's an ester bond, not an amide bond. So instead of dicarboxylic acid and diamine, we have diols. So with the diols, we're going to have our diol, dicarboxylic acid. Same idea. We form that ester bond. We lose the hydrogen from our alcohol functional group, lose the OH. So we're going to have 2N, once again, minus 1 because of the alcohol group on one end and the carboxylic acid group on the other end. So 2N minus 1 H2Os. If we have a single monomer, for example, we have that carboxylic acid group and alcohol. Sometimes with these, you can also get cyclic structures where they kind of join it over both ends. I assume you guys have seen that in some past paper questions. But you can just be forming an ester bond on each side, extend the bonds each way, put the brackets around, n times, because we have this polymer, so that long polymer chain. And once again, n minus 1 H2O, because we have one alcohol group on one end and one carboxylic acid group on one end, so we can have one less ester bond being formed, so one less water molecule, because of the ends of our polymer. So this is a good example of that cyclic molecule, or cyclic, however you want to say it. I think cyclic is the more normal way, but we'll see. So carboxylic acid and the alcohol, guys, smash subscribe. We form that cyclic one, so we form the ester bond with that one single monomer, one single organic molecule, forms essentially around. So we have that ester bond forming. We use the OH here, we lose the H here, so we form H2O, and then we have the ester bond forming. It should be guys, it might be a while still, maybe till 12 p.m., maybe till 12 p.m. We'll see. Ester hydrolysis, guys, acid and alkali ester hydrolysis, both incredibly important, incredibly important. Guys, what do we have to think about with acid hydrolysis? Acid hydrolysis, what do we have to think about? And I'm going to say it. Actually, no. Alkali hydrolysis, because I think the acid one is more relevant for the when we have an amide hydrolysis. Let's see what people are saying. Everyone subscribe if you like alcohol. You can't just write cyclic. I don't know whether you mean cyclic or cyclic. Um, not cyclic, cyclic, not cyclic. Okay. I hear people say both ways, and it just confuses me more. My teacher was Welsh, so she pronounced a lot of things differently, and I wasn't 100% sure the right way to say a lot of things. Okay, exactly. I'm seeing the right things. I'm seeing the right things. We have to be careful of carboxylate salts in alkaline hydrolysis, and with acid hydrolysis, if it's an amide, we have to be careful to form ammonium ions, that NH3+. It may not just be on your nitrogen breaking of that amide bond, there could be another amine somewhere else in the molecule that you're going to have to add a hydrogen to. Okay, perfect. Perfect, perfect, perfect. So, ester hydrolysis, we're breaking this bond here with our carbon single bonded to the oxygen. This alkyl group, we know this part comes from the alcohol, including the oxygen, and then this O8 comes from the carboxylic acid, or the acyl chloride, or the acid anhydride. Carboxylic acid, we need that sulfuric acid catalyst. At acyl chloride, we don't. Acid anhydride, we do not. Checking the stream quickly, guys, to make sure it hasn't blown up yet. Looks like we are all good. Okay, let's continue. So for acid hydrolysis, we're going to have aqueous acid conditions. Oh, everything's lagging for me, guys. Just give me 1 second. 1 second, guys. I do apologize. I was going to ask for the conditions, guys, but okay, let's ask it. NH3 plus always, and yeah. How do we know where it breaks? It will break on this ester bond between the carbon and that single bonded oxygen. That's when we're going to break or hydrolyze our ester. When we protonate in acid hydrolysis and there's an amine and amide present, how do I know if it gets protonated to NH2 or NH3? So this depends what kind of amine we're producing. Okay, I actually do have an example of this, but you'll just add one more hydrogen to what would be. So it may not necessarily be um, NH3 plus if you're bonded to a single carbon. It could be NH2 plus if that nitrogen is already bonded to two carbons. All we're doing is making a fourth bond. Okay, so it's instead of those three normal bonds, there'll be a fourth bond, and that's going to be a plus. So if that nitrogen only has one H and it's bonded to two carbons, that fourth bond that we're making, because we're in acidic conditions, will be we'll just go to NH2 plus because we already have three current bonds. So think about it like that. We're forming four bonds. We're forming that extra bond because we're protonating it. So instead of the normal three, we go to a four. I hope that makes sense. I hope that makes sense. So hydrolyzing our esters in acid hydrolysis, we form the carboxylic acid and the alcohol. So we get hydrogen and hydroxide or H and an OH, hydroxide ion and a proton from our water. So from here, we get that one hydrogen going back to reform our alcohol, and the OH goes back to reform our carboxylic acid. So simple as that, guys, breaking that ester bond with acid hydrolysis. With esters, we do not need to worry about any extra protonation. Yes, it's just making four bonds and adding a sufficient hydrogen. That is perfect. We're about to get to it anyway. For an alkaline hydrolysis, we are going to form that carboxylate salt. So alkaline hydrolysis, yeah, alkaline hydrolysis, same thing, breaking that ester bond, but instead of having an OH, we're going to have a carboxylate ion, which will then become, because we're surrounded by positive sodium ions, it will then become a carboxylate salt. Alcohol will remain the same. Okay? Hope that makes sense. Hope that makes sense. That's a key thing to know. I remember if we had phenol, for example, that would also react with the strong base. So we get that O minus and the Na plus if we had the phenol group attached somewhere over here. Just saying, they may do that in some longer molecule. It is aqueous acid, guys. Okay, aqueous acid. So we're going to have H acids from the acid, but also from the water molecules. Okay, then moving on to ketones, guys. Ah, I meant to show it, guys. I didn't mean to show the thing. I'm trying to make some interaction. Oh well. So ketones, we have a secondary. Sorry, a ketone must come from a secondary alcohol. Secondary alcohols oxidize to a ketone. We do have water as a product because an alcohol is involved in that reaction. Only one oxidizing agent because it's one step. How would you know if the question is talking about alkaline hydrolysis? They will tell you if it's alkaline hydrolysis. They will tell you. They're not gonna. You don't have to guess what kind of hydrolysis. Okay, so to test for a ketone, we use 2,4-DMP. We use 2,4-DMP. What forms a yellow or orange? Different people are taught different ways. Both are fine for OCR. I think even red may be acceptable, but say yellow or orange. Um, yeah, I was taught bright orange precipitate. So when 2,4-dinitrophenohydrazine is dissolved in methanol and concentrated sulfuric acid, it does react with carbonyl groups, aldehydes, and ketones to form that bright orange precipitate. The precipitate is a derivative, a crystalline derivative of the carbonyl compound. Okay, so it's a derivative of the carbonyl compound. Then we're going to recrystallize it. Sorry, We're going to check the melting point to identify the compound. Then we're going to compare it to known, I believe they say data book values, or like book values, known values. That's the key thing. Um, okay, yeah. And we can check the melting point, and then we can compare it to the known values and identify what compound we had before adding that 2,4-DMP. So what are I'm gonna try to ask a question here, guys. Don't even know what my ketone notes are. Okay, I can't even do it. So do we need to know the mechanism for this reaction? My OneNote is famously unreliable. Here are the questions we're going to be doing later, but we do need to know the mechanism, guys, for a ketone with sodium borohydride. So I'm just gonna really, guys, this is on my mouse. If this is horrible, smash dislike. Oh my god. Okay, I'm gonna have to go. There we go. So we have sodium borohydride. This is nucleophilic addition. The hydride will provide those negatively charged hydride ions, those nucleophiles. It's nucleophilic addition. We know we have that polar bond, so our oxygen will be partially negative and our carbon will be partially positive. Okay? Heterolytically break that pi bond with both electrons going to that oxygen because it's delta negative because of that difference in electronegativity. Then nucleophilic, let me see if everyone's happy. Okay. Then nucleophilic addition, curly arrow from lone pairs of electrons, movements of lone pairs of electrons from areas of high electron density to low electron density, going to that partially positive carbon. From here, we have, now what do we have? Because we had that pi bond breaking heterolytically, we have a negatively charged oxygen. We now have formed that carbon-hydrogen bond because of that nucleophile. And we have our alkyl group. Remember, oh, okay, there we go. Oh, my phone is dying, guys. Just gonna quickly put it on charge. Sorry, apologize. Now it's faster? Okay, that's good. Oh, I can't. My charger doesn't reach. That's so big. Okay, I'm gonna end the live just for 5 minutes to charge my phone, and then I'll put it back on. Okay, so from here, we're now gonna form that with the two other alkyl groups, but what are we surrounded by? Sodium borohydride. It's aqueous sodium borohydride. So what we surround by? Polar water molecules. We know water molecules are polar, difference in electronegativities. We have partially positive hydrogens and partially negative oxygens. Heterolytically break this bond. Heterolytically break the covalent bond with both electrons in that shared pair of electrons going to the delta negative oxygen. Then we're going to have lone pair of electrons on that negatively charged oxygen attacking this partially positive hydrogen. You can do these in one step, guys. You can do them in one step. You can do them two if you want, but everything that I'm showing is acceptable in the exam if they ask it. So then we have alcohol. We reduced it. That's perfect there. You have to. You guys can use H plus. I did actually check this in the specification yesterday. I believe you can use H plus or H2O. Both are acceptable. You can use H plus. You can use H plus. I was taught it when I did my A levels like this, so I've kind of just stuck to this. But both are acceptable. You can argue one's easier than the other. It's absolutely fine. Let me just make sure I can quickly delete this all. Okay, this is how we're going to be doing the NMR questions, guys. So I warn you now. I apologize if it is slow. Now it's not letting me delete it. Perfect. Okay, we'll do that in a minute. So continuing on, guys, if we have sodium borohydride aqueous plus our ketone, when we see how much of our reducing agent we need, all we have to do is count the number of hydrogens that we add on to our ketone. So we get one more from this alcohol, then this carbon would only have 3 bonds, so we need to make that fourth bond. This carbon has 4 bonds. We'd also need another, can't see it here, but it need another hydrogen bonded to it. So then from here, guys, if we want to oxidize this secondary alcohol, OH, it'd only be one step to go to that ketone. As we know, we need acidified potassium dichromate, we reflux, and we get a ketone and a water molecule. Why do we get water? Because alcohol was originally involved in the reaction. Okay, that's it. What else do we know from ketone? We can go from a ketone or an aldehyde to a hydroxynitrile. What do we need for this? We need either potassium or sodium cyanide, aqueous, to get those cyanide ions, and H plus ions. Now, we also need to know this mechanism. It's the exact same mechanism as I showed before, guys. Do you guys want me to go through it? Thumbs up if you want me to go through it. If not, thumbs down. This is nucleophilic addition. So I'm just going to talk about this. I hope I'll see the thumbs up by the time I'm done talking about this. So we have our ketone. We add. Now I checked the specification. You can use HCN. Do not use HCN though in general, just because it's toxic. It is toxic. So they recommend you to mix an acid with either sodium cyanide or potassium cyanide. Okay, just because this is dangerous. So we form hydroxynitrile. Do we want the mechanism? Thumbs up. Thumbs up. We want the mechanism. This is very similar. So here, this was also okay. Cool. This was nucleophilic addition. This is also nucleophilic addition, and it's going to follow the exact same logic as before. So let's go for it. Let me see if I can. Oh my god, that's beautiful. Okay. I was getting worried I wouldn't be able to rub things out like this. It would have taken a minute. So what did we start with? We started with a ketone, or we can have an aldehyde. Let's go for an aldehyde. We can have a ketone or an aldehyde. Doesn't matter. This H would just be a second alkyl group. That's what the R is, and R is an alkyl group. What are we surrounded by? We're surrounded by cyanide ions because coming from that sodium cyanide or potassium cyanide. We have that lone pair of electrons. It's a nucleophile, an electron pair donor. Yeah, nucleophile. If it's an electrophile, it's an electron pair acceptor. Know those two. It can help you figure out the name of mechanism if or type of reaction if you forget. So from here we know that oxygen. No thanks. Okay, so we know that oxygen is more electronegative than the carbon, so we get a partially negative oxygen, partially positive carbon. Heterolytically break this bond with both electrons and a shared pair of electrons going to our delta negative oxygen. Okay, what happens? Curly arrow, movement of high electron density to low electron density, or movement of lone pair of electrons. We have these lone pair of electrons on our cyanide ion attacking exactly that partially positive carbon. So where do we go from here? What have we formed, guys? What have we formed? In unseen mechanisms, they like to use this breaking the double bond, I will say, in unseen mechanisms between carbon and oxygen. They do enjoy that. So what do we have now? Because we have that heterolytic fission breaking the covalent bond, both electrons and a shared pair of electrons going to one of the atoms. We now have a negatively charged oxygen, still have that alkyl group, still have that hydrogen, and now we have that carbon-carbon bond to the cyanide ion. Very good if you want to extend your carbon chain, guys. Very, very good if you want to extend that carbon chain. Okay. So I say that's quite important because they tend to ask questions about extending the carbon chain. So you tend to go from a haloalkane to a nitrile, or to a nitrile, or ketone aldehyde to a hydroxynitrile. Very important to extend that carbon chain. What do we have now, guys? Let's go back to our reactants. Oh, okay, back to our reactants. What do we have? Acidified conditions. We are surrounded by protons. You can also use this for your reduction from aldehyde and ketone to an alcohol. Okay. Aldehyde to a ketone, we're surrounded by protons. We have a positive proton, movement from a lone pair of electrons to, movement of a lone pair of electrons, or from a high electron density to a low electron density. So what do we have left, guys? We have that carbon. Oh my god, that should be better bonded to the carbon and better bonded to the oxygen. Make sure your bonds are very clear. Wait, oh my days. What we're going to. I apologize, I'm struggling with the mouse, guys, but I hope it's helpful. And then we have a hydroxynitrile. We have the alcohol functional group, and we also have that cyanide ion attacking that partially positive carbon. And there's your mechanism for electrophilic addition. Sorry, nucleophilic addition. I apologize. Nucleophilic because we have a nucleophile. Nucleophilic addition from an aldehyde or a ketone to a hydroxynitrile. Can we draw arrows like that? Oh yeah. Sorry, I do apologize. Bro, make the lines actually curly. Yeah, they should be more. These two are quite curly. This one's less curly. But yeah, I apologize about that. Let's continue. Continue on. Actually, let me just delete all this first. I hope that makes sense, guys. I hope that makes sense. Nucleophilic addition. Oh, nucleophilic addition. Okay, continuing on, guys. I apologize. I will invest most likely in an Apple Pen or something like that for next year. But here we go. Nitriles, we have a carbon triple bonded to a nitrogen, then bonded to an alkyl group. We can go from a nitrile to a carboxylic acid. A lot of people forget this reaction because on the reaction pathways, it's like all the way down the right. And some people kind of miss it out. What do we need? You can just say aqueous acid, or you can say water and an acid, like HCl. Yeah. So our nitrile, heat and dilute HCl. The dilute implies that we have water into it. But you can't just say water and HCl, both. It's accepted because it's on the reaction pathways, so don't stress too much if you see mark schemes saying weird things. Know the reaction pathways, know what you can put down. So we form a carboxylic acid. It's just something you need to know, guys. Remember this from either a hydroxynitrile or a nitrile. I don't know who Serge is. So reduction, we can reduce a nitrile to an amine. Same thing, guys, if we're going from alkene to an alkane, hydroxynitrile or a nitrile to an amine, you just have to add protons. Okay? So reduction of a nitrile to an amine, we have that hydrogen and the nickel catalyst. It's always hydrogen and a nickel catalyst for alkene to alkane, and any of the either of the two nitriles to an amine. So we have our nitrile, hydrogen. Just add all the hydrogens that we need. So we're going to need two more hydrogens onto this carbon to form four bonds, and then our N will have to form three bonds. So we have NH2. Nothing too tricky. Again, making nitriles, guys. I'm not sure what this is meant to be. This is meant to be a haloalkane, I believe, with cyanide in ethanol. Remember, if we're going from a haloalkane to either a nitrile or an amine, we're going to need ethanolic conditions. It's a good way to think of it. Haloalkane to nitrile or an amine is yeah. Haloalkane to a nitrile or an amine is going to be ethanolic conditions. So we have our hydrogen halide, cyanide ions in ethanol, and we form our nitrile. Nothing scary. This is just nucleophilic substitution. Nothing bad at all. So continuing, we are getting to the end, guys. Getting to the end. Okay, we went over purifying organic liquids. Okay, I'm going to go over purifying organic solids now. Give me a thumbs up if you want me to go back to purifying organic liquids after this as well. I love the debate going on in the chat right now. Can I do the equation for a nitrile to a carboxylic acid? Do you want me to go back up? Nitrile to a carboxylic acid. I'm lost in the sticks. Where is it? Had it somewhere. Wait, nitrile to carboxylic acid. That really long way. So continuing on. So wait. Okay, yeah, we want organic liquid and organic solid. Okay, guys, I need to lock in. Let's go. So going organic solid. So after following your reflux or distillation, quick reflux apparatus drawing out, open system on both the reflux and the distillation. I've heard people say different things about distillation. You do need an open system, or partially open system, so your glassware doesn't crack. That's a fact. I saw some people saying they wanted a closed system in distillation because you have your thermometer where you're going to be collecting your desired product. It will be condensing and going inwards. If we had a completely closed system, the reality is it would blow up. You may potentially, I would check that for sure, but for reflux, 100% open system for sure. In the lab, you need to make sure there is some airflow so glassware does not crack. But I would check the distillation thing. I'm pretty sure we were told partially open, but be careful. So an open system to avoid the pressure buildup for the distillation. We have our condenser, water in at the bottom, water out at the top. We have our round bottom or pear-shaped flask. We have heat going up. Remember, we don't use a Bunsen burner. We use a water bath or a heat mantle to control the temperature. How do we know when it's separating funnel or the min volume of hot solvent? We're going to go over that now. We also have anti-bumping granules to prevent violent oiling, sorry. So our Buchner flask, you actually don't need to say Buchner flask in your exam. They tend to just want filtration under reduced pressure. Let's look at the apparatus. We leave our sample on the filter paper and we're filtering under reduced pressure. This allows the sample to dry. From here, we're going to rinse the solid to remove soluble impurities. So we rinse the solid on filter paper to remove the solvent and soluble impurities because you're going to wash it off. So anything soluble will go down through the filter paper as they will dissolve and then go with your with the liquids that you're washing with down through the filter paper into your flask. Exactly. Separating funnel is liquid, hot solvent is for solids. Okay. So this is just a little diagram of a Buchner flask. You should have an arrow here going filtering under reduced pressure. But those are the key two diagrams. So recrystallization, purifying the organic solid. So exactly that. Some organic solids are soluble in hot solvent. This is what we do. When it's insoluble, some organic solids are soluble in hot solvent, but insoluble when the solvent is cold. Therefore, when we cool it, a precipitate will appear. So here are the very, very key points for your exam, guys. Like I cannot stress, you just need to know these few bullet points. So we have to dissolve the organic solid in the minimum amount. Minimum, I'm sure your teachers have been telling you this a lot. Dissolve the organic solid in the minimum amount of hot solvent. We then filter to remove insoluble impurities. Insoluble, guys. So it's dissolved. Put that liquid through with our dissolved desired organic solid, but it's dissolved, and we get rid of any insoluble impurities. From here, we cool it a bit. You can use an ice bath, whatever you want. The organic solid will precipitate into the solution as it cools, because as we established, in this solvent it's soluble when hot, but insoluble when cold. So as we cool, our organic desired product will start to form again. Once it is cooled, we filter a recrystallized sample to remove those soluble impurities under reduced pressure. So exactly as we said here, guys, we kind of wash it over, so all soluble impurities will be removed. Then we have to wash it with cold water, so that's to remove those soluble impurities, once again, and any impurities in general, and then we dry it. So you can say it in an oven, but you don't have to. Then post recrystallization, you can dry your sample, measure the melting point, compare it to the data book values to assess purity or identify your compound. Hope that makes sense. Guys, do we want to Google it right now? Do you want to Google the OCR specification and see whether it's closed or open? Because I've seen different things. I, I I think it could be closed, you know. Unsure, but some part needs to be left open. Otherwise, we crack glassware. Doesn't the reduced pressure thing takes place before it's dissolved in minimum volume? No, the filter on the reduced pressure is after we form that precipitate after it cools. These are the steps, guys. Dissolve organic solid in minimum amount of hot solvent, then filter this to remove insoluble impurities. Then it will cool. You can use an ice bath. Your organic solid will precipitate into the solution as it cools. From here, once it's cooled, you can filter the recrystallized sample to remove those soluble impurities by washing cold solvent over it under reduced pressure. So you wash it with cold water and then you dry. Then post recrystallization, same idea with that 2,4-DMP where we can measure melting points and compare to known data book values. We dry the sample, we measure the melting point, and we compare it to those known values to identify the purity or the compound. Does that make sense, guys? Should we Google it right now? Yeah, why not? Let's check. Let's check the specification. Let's check the specification right now, guys. Like, why get lost when we can literally just ask the source, right? So if we see distillation, I mean, it might not even tell us, guys. It might not even tell us. So we need to know the setup. Let me know if this is okay, just me going over the specification, guys. I feel like it can help sometimes. This is how you find out what you need to know. And then remember with that organic liquid, guys, we have those anhydrous salts with the organic liquid. That was purifying organic solid. I'm not seeing too much whether it's an open system or not. Let's just ask Google. Is distillation? Oh wait, there we go. So guys, this is what Google says. This is what Google says, guys. Are we all good? Guys, give me a thumbs up if we're happy with this. Partially open system or open system for this transfer. Are we all happy? Are we all happy? How about this? How about this? At the top. Can you even look at some images, guys? Should we check OCR? I mean, these practicals tend to come up. These practicals do tend to come up. Guys, let me know if we're happy with this. If you want me to keep going back onto the notes, let me know. But I feel like it's key to know. There's a lot of confusion, and we don't want people to be confused, do we? So here, guys, we do have a bung here. Here we do have a bung. So that's just great. This is OCR GCSE science. Okay, it appears to be we need a bung, guys. So the partially open system is at the end here. So I guess the partially open system. Okay, yeah, distillation we do have. I'm seeing a bung. I'm seeing a bung here. This probably has quite useful information. Okay, guys, are we happy? So it looks like they're closed. It looks like they're closed, guys. Distillation is closed. Okay, so the open system is at the end where we're removing our desired product, and they're closed at the top. So when we say the partially open system, I mean, we can just see here. Should we check save my exams, guys? Sorry if I'm wasting time. If you want me to, no, reflux is definitely open. Reflux is open. So there you are, guys. There you have it. It is closed for distillation. I apologize. It's closed for distillation. To avoid the pressure buildup, this part is open where we're collecting the desired product. Reflux is always open. Reflux has no debate. No confusion with reflux. Yeah. We have a bung for distillation at the top, guys. But then the partially open bit is just here. So we don't get that removed glassware. This is for OCR. There we have it, guys. Is everyone happy? Is everyone happy? Thing is, I've seen mark schemes say different things, or they say ignore. So it's a little bit, but now we know. And make sure this is actually quite important. This bulb should be right where we have that collection of our desired product. Hope that makes sense, guys. Partially open the end, closed at the top. There you have it. You will have to draw this, guys. So I'm happy we clarified this. I am happy we clarified this. Okay, guys. So that is purifying organic solid. Now, quickly going back to purifying an organic liquid. So purifying an organic liquid, guys. Same thing. Following our reflux and our distillation, we add water to the mixture. Is everyone happy with the fact that we just Googled it and clarified? Are we good now? Guys, give me a thumbs up and smash subscribe if you're happy with that. So following our reflux and distillation, we add water to the mixture. We place it in a separating funnel. We shake it to settle in an aqueous and an organic layer. We collect the organic layer. It's not always the bottom layer, which is organic or aqueous. Okay, we have to check density information they give us in the question. From there, we add a drying agent. This can either be anhydrous magnesium sulfate or anhydrous calcium chloride. These bind to any water present. Okay, we can then remove by filtering. We can remove these drying agents. They're not going to be anhydrous anymore. They would have binded or bound, I guess, bound to any water present. So we filter the mixture to remove the drying agent. Then, to purify, we redistill the sample. Normally in the mark scheme it says you can or may not have to do this bit. Normally this bit is enough, but normally say redistill the sample, heat to your boiling point of your desired organic liquid, and collect it. Now we've established we have that bung at the top, but the reason naturally to collect that desired product, that bit will be open, and you do have to say sometimes we want to avoid cracking glassware and pressure buildup. So that's purification of an organic liquid. Alright, guys, I believe we're almost done. Two more amide hydrolysis, guys. Very similar to ester. If anyone new is joining, let me just make sure the stream is alive. Stream is alive. That's perfect. Amide hydrolysis. Same thing with the ester. We break that amide bond. So we break that bond between the carbon and that single bonded to the nitrogen. Yeah. So we break that. Here we have a secondary amide. Why is it secondary? Because because the nitrogen is bonded to two carbons. Carbon bonded to the oxygen and this R dash alkyl group. We have R and R dash. This is just saying that these alkyl groups could be the same, but they could be different. So here we have our amide. We break the bond. If we are in acidic conditions, as we established, we're going to protonate. We're going to form ammonium ions. Okay, so we're protonating our amine. So here, we would normally just have the OH from, lagging a bit. Okay, there we go. We would normally just have reforming that carboxylic acid, the OH here, and one proton going back to form our amine. However, because it's acidic conditions, we have four bonds now to our hydrogen, to our amine, sorry. So we protonate it and it gains that positive charge. Once again, the key thing is just protonate it to do whatever to form four bonds. As we had the question before, whether it's two hydrogens or three hydrogens, doesn't particularly matter as long as you have those four bonds for that extra proton being added to get that positive charge. So we have amide hydrolysis in acidic conditions. If it's alkaline, what do we have? Oh yeah, I wanted to mention, guys, with this alkaline hydrolysis of both esters and amides, you have to be careful that if we have a haloalkane on the chain as well, we will also undergo nucleophilic substitution. Thumbs up if you want the mechanism for that nucleophilic substitution, guys, from a haloalkane to an alcohol. Thumbs up if you want that. I'm going to go through this, and then if I see thumbs up, I'm going to do that. So alkaline hydrolysis, we break that amide bond. Then we form that carboxylate salt or the carboxylate ion, which will then attach to those positive sodium ions. We have heat and aqueous sodium hydroxide. So we form that carboxylate salt, but then because we're in acidic conditions and we know that amine is a base and we're in alkaline conditions, base and alkali do not react. Yeah. Remember, the way to think of it is we know in the acidic conditions, we're going to react with our base, which is that amine because of that lone pair of electrons. In the alkaline conditions, we're going to react with the acid, which will be here, the carboxylic acid. So we form that carboxylate salt, and then we form, in this case, a primary amine. Hope that makes sense. I'll quickly go over the mechanism for a haloalkane to an alcohol. Guys, tell me what type of reaction it is. Tell me what type of reaction it is. So if we have a haloalkane, let's just make this a bit easier and skeletal. Haloalkane to an alcohol. We know we're surrounded by sodium hydroxide, so we're surrounded by sodium hydroxide ions. What type of reaction is this, guys? What type of reaction is it? So here we have a partially positive carbon, partially negative chlorine, because the chlorine is more electronegative than the carbon. Nucleophilic substitution. Yeah. Okay. Nucleophilic substitution, exactly that. Why? Because we have a nucleophile and we're substituting something. Okay. So we're going to have heterolytic fission. Both shared pairs of electrons, or both electrons in the shared pair of electrons, will go to one of the bonded atoms. So we're going to form chloride ion. Then we have the movement of a lone pair of electrons shown by curly arrows, go from an area of a high electron density to an area of low electron density. So all we have is we have our alcohol and we have our chloride ion. This could be bromide ion, it could be an iodide ion, whatever it is, that's it. Nothing scary at all. Okay, I have all these tabs open now. Let me close a couple. Okay, all right. Exactly as I said, watch out for those other reactions on the chain when doing this alkaline hydrolysis in general. Okay, I believe. Okay, last point, guys. I'm not going in depth into chromatography. I just have some key points that I wanted to cover about chromatography. I hope that's fine with you guys. You can always just use the revision guide if in doubt. Okay. So some key points about this and TLC chromatography. It's used to identify organic molecules. We have a liquid stationary phase. This separates the compound by relative solubility. The more soluble, the more time it's dissolved. So if this is gas chromatography, the more time dissolved in that viscous liquid in the tube, the longer time it will take to travel through the tube to the detector. That's for gas chromatography. Now, calibration curves. They tend to not ask this. They could ask it this year. So what is a calibration curve? It's a curve relating heat areas to concentration when we look at the results of our gas chromatography. Okay? So how do we make it? We prepare several standard solutions of known concentration. We obtain the gas chromatograms or chromatograms for each standard solution. Then from there, is everyone happy? Then from there, we can plot a calibration curve of peak area against concentration, and then we can use this to identify the concentration of certain compounds. The time taken tells retention time. You can use this to identify the substance. The area under each peak is proportional to the relative concentration of each component. These are just key points with gas chromatography. Okay. The mobile phase is the mixture of gas, the carrier gas that we put in, and the stationary phase is that high boiling point liquid coating our column. Okay, and that is the thing that our gases will dissolve into if they're more soluble. So, guys, what are the three things that affect retention time? I have already said one of them, but what are the three things that affect retention time? If you can tell me the three things that affect retention time and potentially any problems with both RF values and retention times when trying to identify substances, that would be great. That would be great. Let me know, guys. Let me know. Chromatography is like the large data set. Guys, smash subscribe if you hate the large data set. Let me know. Let me know. Three factors affecting retention time. It's very slow for me. So, solubility, exactly. I'm going to go through them because the chat is very slow for me. It'll come up as I go through. So solubility, the more soluble, the longer time it is in the tube. The boiling point, a higher boiling point, spends more time as a liquid in the tube. Therefore, it will also take longer. The retention time will be longer. And then exactly that, the temperature of the gas. If the temperature is incredibly high, everything will remain as a gas because you'll be above their boiling points, and then everything will go a little bit faster. So exactly that, relative solubility, the boiling point, and the temperature of the gas. The problems with gas chromatography, they may ask this, also TLC, is some substances may have a similar retention time or RF value, so we can't differentiate substances. I believe that is all the content that I prepared. Oh yeah, and then here we have our gas chromatography setup, I guess. So let me know if you guys have any questions. I'm going to leave up these notes for a second. I'm going to go through one NMR question and a few other questions from predicted papers. If it's more soluble, it will be a longer retention time or greater retention time because it spends more time in the stationary phase. Exactly. It'll be dissolved into that liquid that we have coating the tube, so we'll spend more time there. It's a viscous liquid. I believe it can be oil, yeah. I mean, for gas chromatography, there's a few things you can say. It can be dissolved. It can be oil, but it also can be any viscous liquid. Really, they could adapt it to the question. But yes, it can be oil. It tends to be oil actually. I think that is the default that they tell you in the specification. But viscous liquid is also fine. Guys, we're gonna go over a few questions now. I've got a few questions. I'm gonna kind of leave it up for a second if you guys want to have a go. This is from it's from a YouTube. I'm trying to remember. You guys may have seen this before, but we're just gonna fill this in. So first we're starting. What do we have? We have a halo alkane functional group. In this case with a chloride, and then or chlorine atom, and then we have an OH. First step. First step would just be with sulfuric acid slash. In this case, it was sodium dichromate, but we know potassium dichromate is the same thing. Don't get intimidated if they throw a curveball like this in the exam. So what happens here? Well, a haloalkane will not react, however, our alcohol will. It's under reflux. This is a primary alcohol because it's connected to one carbon. So connected to one carbon, what do we know? If we're under reflux, we're going to be going to a carboxylic acid. Remember, we would only be forming one water because only one of these reactions has an alcohol involved. Aldehyde to a carboxylic acid does not form water, so we'd have two oxidizing agents in our equation, but we would only have one water. Okay? Nothing scary there, guys. Nothing scary there. How about the second one, guys? What are we forming? We currently have a carboxylic acid. We have that chlorine atom with SOCl2. What are we forming? What are we forming? We are forming an acyl chloride, as we know. What are the products when forming the acyl chloride? Well, let's see what we lose. We lose the OH. We lose one of the chlorines here. So we currently have SO. We're going to have SO2. And then as we know, when we use acyl chlorides, we tend to have HCl as a product. Does that make sense? OH, so we have the two oxygens there, the one S there, we have one chlorine remaining, and the hydrogen that we lost from the carbon. SO2 and other. Perfect, acyl chloride. I'm seeing all the right answers. Now here, guys, nothing tricky. I'm not going to waste your time here. This is a little bit of acylation. As we know, when we have an acyl chloride, reflux, halogen carrier with benzene, we will form. In this case, this is 2-chloro, 1-phenyl, ethan, 1-one. Don't get too intimidated by that. The reason it is because this is our primary, so this is our carbon number 1. You can label our carbons. That's carbon number 2. So on carbon number 1, we have that phenyl group, the benzene. Chlorine goes on that second group, and because it's the ketone, we also have on that first carbon the own suffix. So all we need here, fine. All we need here is a benzene ring because we already have that halogen carrier to form the electrophile in this acylation. What are the products, guys? What are the products? What would the products be here? What do we lose? We lose this chlorine, and we're also going to lose the hydrogen that was attached onto this carbon. So we're going to have HCl. As we know of acyl chlorides, tend to have HCl as a product. Let's not revise. Why is benzene? Yeah, guys, my benzenes are disgusting. They're famously disgusting. Okay. So from here, what do we have here? We have an acyl chloride and we have a chlorine. We have to go to this. So what are we forming, guys? What are the functional groups that we're forming? Well, nothing along here. We're forming an amide bond. We have a nitrogen bonded to a carbon and then double bonded to an oxygen. So what do we need? Well, we have our acyl chloride. Yeah, exactly. We have our acyl chloride. Then we're going to this massive compound here. We have, oh my days, my benzenes are horrendous, guys. I do apologize. I'm just going to draw a small tab space. So we have our two methyl groups here. And then what do we need? We know we lose one hydrogen. It's going to be NH2. The same way we lose one hydrogen from an alcohol when forming an ester bond. When forming an amide bond, we lose one hydrogen from our amine. Yeah, thank you for the benzene compliment. So this is what we need to form that amide bond with the acyl chloride. Then everything else is the same because we can see we have the two carbons here. Let me go back for a second. We have the two carbons here. That's exactly what we still have from our original organic molecule with the chlorine and our acyl chloride. So nothing scary there. Nothing scary there. Forming that amide bond from our amine with attached to the benzene ring and the acyl chloride. Now we're in excess diethylamine and ethanol. So diethylamine, let's draw that out. So what do we have for diethylamine? We have a nitrogen. We know it's going to have three bonds, so ethyl groups on each one. So 1, 2, 1, 2. We have our diethylamine. Then from here, guys, what reacts here? What reacts here? Let me know what reacts. Benzene 2, yeah. Perfect. What reacts here? What's our product going to be? Or like, what's the functional groups that react is what I'm trying to say. We have ethanol. That could give you a little clue, potentially. So we know when we have ethanol, we're going from a haloalkane to either an amine or a nitrile. Now, because we're reacting it with an amine, not a cyanide ion, it's going to be going to an amine. Okay, haloalkane to an amine. Okay, I'm not going to draw, you know what, I won't draw it all. So drawing out all the benzene with our methyl groups, everything else will remain the same, nothing else will change here. Because we know the diethylamine and ethanol, we are only affecting that haloalkane. So going down, going across, now instead of this chlorine, we're going to be attached to the nitrogen, and then we just have to draw in these ethyl groups. Nothing scary, guys. Haloalkane to an amine, perfect. That's exactly what we have here. Thumbs up if we're happy with this, thumbs up if we're happy. Smash subscribe. So I believe this was a predicted paper, I think from, I can't even remember. This is another predicted paper. Okay, everyone's happy? Guys, thumbs up if we're happy with the last question. I'm going to start going through this one. So we're told that methyl benzoate can undergo nitration. Okay, nitration of benzene, we want to see this tomorrow. Nitration to make methyl 3-nitrobenzoate. Just making sure the stream isn't crashed because we are very hot right now. Guys, I'm just going to pull the TikTok back up before we start this next question. Just going to pull the TikTok back up, just try to get any viewers that we can. To respect the husband. Let me know if that makes sense. Electrophilic substitution, exactly. That's exactly what's going to be happening here. Nitration of benzene. Electrophilic sub, electrophilic sub. Give me 1 second, guys. Feel free to have a go at this question, and I can tell you now, the next part will be to draw the mechanism. I'll leave the question up if you guys want to have a go. Just give me 30 seconds. 30 seconds, guys. I apologize now. Feel free to have a go at the question. Okay. All right. Perfect. Yeah, the benzene mechanism should be seen as free marks. It should be seen as free marks. So name the mechanism for the nitration of methyl benzoate to methyl 3-nitrobenzoate. Exactly, nucleophilic substitution. I'm just going to write NS because it's hard to write out with my mouse. So to draw the mechanism of the nitration of methyl benzoate to methyl 3-nitrobenzene. Okay, nothing scary. We have to show how sulfuric acid acts as a catalyst in this reaction. So same thing as always, guys. Do not stress about this methyl benzoate. Okay, do not stress about all of this group here. Don't worry about all of that. Just focus on getting that nitration of benzene. Okay, because this doesn't do anything specific know it's going to be on carbon 3. Okay, so we know it's not going to be on carbon 2, 4, or 6 because we don't have electron donating groups, but in general, we do not have to stress too much. So nucleophilic substitution, forming the electrophile, we know. I'm going to do my best to draw this out, guys. Let me know if it's horrendous. Smash this like if it's horrible. So I'm going to do this in one equation this time, guys, just so I can save myself. So we have that sulfuric acid catalyst with nitric acid. What do we form? We form that HSO4 minus that will be reformed later because it's a catalyst. We form the electrophile that we need, that NO2. And then what else do we form? So what do we have left, guys? What do we have left? So form that. So we would have H2 NO3 plus. We form that NO2, so we have H2O left. Nothing scary here, nothing scary here. So now we have that electrophile that we need, right here, that NO2 plus. So oh wait, yeah, sorry guys, electrophilic substitution. I apologize. Electrophilic substitution. Benzene will always be electrophilic substitution. Electrophilic substitution, guys. Always electrophilic substitution. Sorry, apologize. Okay, so from here, we have our benzene. So it would be that methyl benzoate. So we can just write that on, methyl benzoate. We have that C double bonded to an oxygen, single bonded, okay. Double bonded to an oxygen, single bonded to another oxygen, and then that is bonded to a CH3. I'm just going to leave it skeletal. And drawing the mechanism out, what is our electrophile? Is that NO2 plus. Same for every single electrophilic substitution, guys. With benzene, we go from that delocalized ring of electrons, high electron density to low electron density, to the electrophile. Okay, so what do we have from here? We're going to have that horseshoe. We are indeed going to have that horseshoe. So which carbon are we attacking? We're attacking that third carbon. Okay, just quickly drawing this on, guys. I apologize if it's not neat, but this is not the relevant part of the mechanism. So we have that horseshoe. Remember, it has to be covering majority of the other carbons. This is not the prettiest diagram, but I hope you guys get the idea. Then we have that hydrogen, and then we have that NO2 electrophile that we just attacked. Then we have that heterolytic fission, both electrons in the shared pair. Guys, yeah, it's electrophilic substitution. I apologize, I meant electrophilic. So heterolytic substitution, we break this carbon-hydrogen bond with both of the electrons going to reform that delocalized ring of electrons, pi system, whatever you want to say, or pi ring, all of these are fine. What are we left with? Well, this is perfect. We now have exactly what we need. So just drawing out, finishing the mechanism, we have that NO2 on the third carbon, exactly as we needed. Ring fully restored, plus a H+. But then we know we're going to have to reform our catalyst. Our catalyst was sulfuric acid catalyst. So reforming the catalyst, guys. Reforming the catalyst, we have that H+. Guys, let me know if these live streams are not useful. I apologize. So we have that H+, adding that HSO4 minus, because we have to reform that sulfuric acid catalyst. And then, perfectly, we have our catalyst reformed. We have that H2SO4, catalyst reform. Nothing scary with this mechanism, guys. That's perfect. The only mechanism you need to know for benzene is electrophilic substitution. Unless it's an unseen mechanism, then they may do something weird, but it should be electrophilic substitution because we know it can't be electrophilic addition due to that spread out electron density above and below the carbon plate. But yes, it will be electrophilic substitution for A level. So guys, next question. We're told that 3-hydroxybutanoic acid, so 1, 2, 3, 4, butanoic acid, 3-hydroxy, so it's a 1, 2, 3. So here is our organic molecule. Can also form other substances. Describe how 3-hydroxybutanoyl chloride, so butanoyl chloride, we have an acyl chloride, 1, 2, 3, 4, 3-hydroxy, this is our first, quickly numbering our carbons, we have 1, 2, and this is going to be 3. So then we have that 3-hydroxybutanoyl chloride can be prepared from 3-hydroxybutanoic acid. Carboxylic acid to an acyl chloride. What do we need, guys? What do we need? SOCl2. That's what we need. If we're going from a carboxylic acid if we're going to an acyl chloride from a carboxylic acid, and any safety precautions that need to be taken. So we need SOCl2. Safety precautions that need to be taken. We need to be in a fume cupboard. I believe that is the correct terminology. I think there's different things you can say. Why do we need to be in a fume cupboard? So quickly reminding ourselves of the products. If we have, let's just draw out the equation very quickly. So we have our, you know what, let's draw it up here actually, just to make things a little bit more efficient. Oh, it's not letting me. Okay, fine. So quickly just drawing out that equation, guys. SOCl2, perfect. Use a fume cupboard. Toxic white fumes, exactly that. HCl is our product, is one of our products, and these are toxic white gas or toxic white fumes. Perfect, perfect. I'm gonna quickly draw out the reaction equation just to remind you guys. 2, 3, 4. There's a hydroxy. That should be bonded to the oxygen, guys. Make sure your bonds are clear. I'm just on a mouse. I apologize in advance. 1, 2, 3, 4. Plus SOCl2. What are we producing? And what do we know? We're going to lose this OH because we're going to an acyl chloride. And we're also going to lose one of the chlorines here. We form the SO2 plus HCl. Yeah, I upgraded to a mouse, guys. I bought a mouse yesterday. Okay, and then we have exactly what we need. And they asked in the question, there's 3-hydroxybutanoyl chloride. 3-hydroxybutanoyl chloride. Okay, now on to the next question. We have two more, and then we have an NMR question, guys. Nitration of benzoic acid. What position? Nitration of benzoic acid. We have to think whether it's electron donating or electron withdrawing, and then from there we can determine. Benzoic acid is a withdrawing group, so it's going to be 3 and 5. Carboxylic acid is withdrawing. Remember, OH and NH2 are donating, and NO2 is withdrawing. And if we have a carboxylic acid group, they tend to tell you in the question that they will be withdrawing. Okay, so now we have an acid anhydride, guys. It's an acid anhydride derivative of 3-hydroxybutanoic acid. It's shown below. So here's our acid anhydride. The acid anhydride derivative is more reactive than 3-hydroxybutanoic acid. Draw the products that are made when this acid anhydride is reacted with ethanol. So as we know, we're going to have to break the bond in our acid anhydride. We're going to break this bond right here, guys. And what are we reacting it with? We are reacting it with ethanol. 1, 2, and we have our OH. So what are we forming? Well, we know we're going to be forming an ester bond. Ester bond and the carboxylic acid. So we're going to lose this hydrogen from our alcohol, form the ester bond. So let's just draw it out. So focusing on the left-hand side here, we have 1, 2, 3, double bonded to the oxygen. Then we have our OH here. Then from here, single bond to the oxygen, where our ethanol is, and then we have 2 carbons. Guys, name this ester, or what does it say here? It does not say here. Name the ester, guys. Name the ester. Exactly, ester carboxylic acid. Electron withdrawing, electron donating. Electron donating will partially delocalize its electrons into that benzene ring, increasing the electron density, making it more susceptible to electrophilic attack. Electron withdrawing will do the opposite. And because with electron donating, carbons 2, 4, and 6 increase in electron density, so those react. Electron withdrawing does the opposite, so carbons 3 and 5 will be more likely to react. I think the key thing with the carboxylic acid is the idea, because you have that OH and that double bonded oxygen kind of bonded to the benzene, or to the carbon bonded to the benzene. Yeah, these will be essentially, because those oxygens are electronegative, those are going to be dragging those electrons away from that carbon. Just think of it like that, because they're more electronegative. So you are withdrawing that electron density from the benzene. Because you have those oxygens above, it's withdrawing it away, if that makes sense. So let's see what people are saying. Ethyl, 2-hydroxy. It'll be 3-hydroxy, guys, if we number the carbons. This is our first priority carbon when looking at. So we're going to have 1, 2. It's going to be ethyl, 3-hydroxy. So we first do our alkyl group that comes from the alcohol. So it's going to be ethyl, 3-hydroxy, then 1, 2, 3, 4. So it's going to be butanoate. Ethyl, 3-hydroxy, butanoate. So you have to do the alkyl group first when naming your ester, and then we focus on the carbon chain, which is bond on the side of the carbon double bonded to the, yeah, you have to say ethyl first. Ethyl, 3-hydroxy, butanoate. Ethyl, 3-hydroxy, butanoate. So once again, guys, if we want to quickly go down to naming those esters. For example, here we have this 1,2,3, this propan. We have 2-methyl, because this is our priority functional group, the ester functional group. 1,2,3,4, longest carbon chain is butan. It's going to be butanoate. And we have 2-methyl because it's on the second carbon, as this is our first carbon, which has the highest priority functional group. Hope that makes sense. And then from here, guys, what else do we have? Well, we know we lose this hydrogen from our ethanol, so we're going to be forming our carboxylic acid. So essentially the rest of the molecule on this side here, okay? So we have that OH, double bonded to the oxygen, and we go down, up, OH, then down like that. Just filling out the rest of the molecule. Nothing scary. It's always your alkyl group first with the ester. This is not about alphabetical. Alphabetical is relevant for other molecules, but for this, it's about doing your alkyl group first. That's bonded to that single oxygen, the oxygen that's bonded single to the carbon. With esters, you always do that alkyl thing first, because otherwise that 3-hydroxy would be referring to that OH group on your alkyl group bonded to the oxygen. If you put 3-hydroxy at the start, there's confusion, and you would think you're talking about the oxygen bonded, oh sorry, this chain bonded to this oxygen, single bonded to the carbon on the right hand side. I hope that makes sense, guys. I hope that makes sense. Give me a thumbs up, smash subscribe if that makes sense. Oh, horrible. Okay, so from here, next question, guys. I appreciate that. I appreciate that. So step 2, let's look at what we have. Have an amide bond here. This is a secondary amide or tertiary amide because this nitrogen is bonded to 3 carbons. So we have a tertiary amide. Yep. Step 2 produces substances X and Y. We're going to have to name Y. Identify the type of reaction that step 2 is, and identify the reagents and conditions required. So guys, what we're saying, we can see we're producing a secondary amine, and we're going to have to do something else. Let me know, let me know, let me know. Making sure the screen hasn't crashed. We have not crashed, awesome. So what type of reaction is it? Alpha is on it, alpha is on it. It is indeed alkaline hydrolysis. Why do we know it's alkaline hydrolysis? Because we don't have that extra 4th bond on our amine. We don't protonate that amine. It doesn't get a positive charge. So we're not going to be in acidic conditions. So exactly that, guys. It's going to be alkaline. It's horrendous. Alkaline hydrolysis. Try to write this out. Okay, alkaline hydrolysis. What do we need? Sodium hydroxide. Aqueous. Okay, this is actually getting horrendous, so I'm just going to leave it there. And you need heat. So what bond are we breaking when we're breaking this amide bond? We're breaking just here. So we have that secondary amine. Draw the displayed formula, guys. In this case, they want it displayed, which is a little bit frustrating, but that's okay. So we have starting from the left-hand side, we have our CH3, and we know we're going to be forming a carboxylate salt. Okay, why? Because we are surrounded by these sodium ions. In alkaline hydrolysis, that OH on our carboxylic acid will lose the proton and become carboxylate salt. Amine and alcohol, or amine and carboxylic acid? Oh, I meant that. If I said alcohol, I meant carboxylic acid. Sorry, guys, I've been talking for a while. If I trip up on my words, I apologize. But I'm drawing out the correct things here. So that carbon double bonded to the oxygen, and then we form that carboxylate salt because we're in alkaline conditions. Very key to remember, guys. So for part III, we're told the student said step 2 can be replicated by heating this DMAC or DMAC with dilute hydrochloric acid. Why is he incorrect? We know he's incorrect because, as we already mentioned, that secondary amine would become an ammonium ion. So we'd have our CH3s, we'd have our proton we had before, then we then have another proton, and it would get a positive charge because we're in acidic conditions. Yeah, so we would not get the same 2 exactly because nitrogen has 3 bonds exactly. If it was an acid, it would have 4 bonds and positively charged. Perfect, amazing. And that's what you need for these questions, guys. How do I know that it's alkaline hydrolysis? I don't understand. Because, okay, we know it's alkaline hydrolysis So first of all, if it was acidic hydrolysis, the amine that we produce would become protonated. There would be another hydrogen bonded to it and would gain a positive charge. Because we know amine is a base, so if we're in acidic conditions, it becomes protonated. Because, why is it a base? It has that lone pair of electrons. So it is indeed a proton acceptor because of that lone pair of electrons. Because if it was an acid, it would get a proton. Exactly. Yeah. So therefore, it has to be alkaline hydrolysis. And the student is incorrect for the same reason. Because if we want this product, we have to be not in acidic conditions. And that's exactly it, guys. I hope that makes sense. Last question of the day, guys. Last question of the day is an NMR question. So this is a little warm up for later on. So guys, I have a table pre-drawn out for NMR. We have our number of hydrogens slash the relative intensity, the splitting pattern, and I'm also going to write down the adjacent number of hydrogens. Remember the n+1 rule. So if we have a triplet, it will be 2 adjacent hydrogens. For a quartet, it will be 3 adjacent hydrogens on carbon atoms. So yeah, we have a chemical shift, and we have the suggested group or section of the molecule. I know sometimes people write this out into two columns, maybe like the group and then the suggested molecule or section of the molecule, but it doesn't really matter. This is the last question of the day, the live tonight. Guys, I can tell you right now, the NMR questions that we're going to be doing, I believe these two are past paper questions. This is from 2024. I believe the one we're doing now is past paper. And then all the other ones, I have the mark schemes down here, and all the other ones are either not past paper or they're similar to past paper, but not quite. Guys, give me a thumbs up if we're happy with the NMR. I hope this is helpful. Let me know if the stream is completely useless, but we're going to do a bit of NMR here. I know everyone wants to hit on NMR, so that's what we're going to be doing. So first, we have to find the empirical formula in this specific question. I'm going to whip out the calculator. So the way we do this, this is going to be annoying to type. Okay, I apologize in advance. So we have our carbon, we have our hydrogen, and we have our oxygen. So for our carbon, we can treat these as the masses, guys. We do 54.54. Oh my days. 54.54. Remember, this is to find the empirical formula. 54.54, 9.1, and our oxygen to be 36.36. These are going to be very rough, guys. We divide each by the MR. Oh, guys, I do want to go back over the CIP rules after this question, just to make that also very clear when finding your highest priority groups, but I'm just going to go over this now. So 36.36 divided by 16. Okay, so do we want to plug this in the calculator? Let's do it more or less. So we have 54.54 divided by 12. It's going to give us 4.545. 4.545. 9.1 divided by 1 is just 9.1. Then we have 36.36 divided by 16 is simply 2. I'm sorry, you guys will be faster than me just because I have to do it writing it out. So we're going to divide by the smallest number, which is 2.275. So we have 5.45 divided by 2.2725. You could store the answer if you want to make things a little bit quicker. So we're going to have 2 carbons. This will give us 4 hydrogens, and this would give us, well, we divide it by 1. So each of these will be divided by 2.725. Let's just call this A, just to make it clear. Well, that's not clear at all. We'll call this A. You can store it in your calculator as A if you know how to do that. Divide each one by A. That is not an A. And then we get 2 for 1 as the empirical. We're told that the molecular ion peak, well, we have one at 132. So 132, we can take the MR to be 132. So right now, we currently have the empirical formula to be C2H4O. So let's quickly find the MR of that. We do 2 times 12, answer plus 4, answer plus 16. That is 44. But we know the total MR. Let's see if everyone's happy. Yeah. So from here, 132 divided by 44, 132 divided by 44, we get 3. So we're going to have to multiply all of this by 3. So we're going to get, for the molecular formula, be C6, 4 times 3 is 12, and then O3. Okay? Nice. C6H12O3 is our molecular formula. Let's work from there. So they don't actually give us any infrared in this question, which is quite interesting. So let's work through. Let's start filling out our table, guys. Do they give us this proton NMR in D2O? D2O, proton exchange. We use D2O to remove OH or NH peaks. Okay, that's very important, guys. So these are puzzles, guys. You do have to kind of like work through it. You'll be able to do this quickly in the exam. Will just take me a second. So let's go from left to right, or sorry, right to left. So looking at our lowest chemical shift, we have three hydrogens and we have a doublet. So let's fill that in. We have three hydrogens, we have a doublet. Therefore, there will be one proton on the adjacent carbons. Chemical shift, where are we at? Both of these are 1.2 and 1.3. Okay, so let's write that in. It doesn't particularly matter because they're both going to be alkyl groups. Just to confirm, guys, we are going to have that alkyl group. Hydrogen bonded to a carbon, bonded to an alkyl group. Okay, nothing scary there. So continuing on. So let's just fill out both of these first because they're both going to be alkyl groups. So what do we have? We have six hydrogens and we have a singlet. Six hydrogens and a singlet. So singlet, n+1 rule, we're going to have zero hydrogens on adjacent carbons. So from here, we already know with these six, it's very likely, let me draw this very carefully. So I'm going to draw the hydrogens that we're looking at in black, and then I'm going to draw potential other hydrogens in red, okay? So because we have six in the same environment, and they are bonded to a carbon which has no hydrogens onto it, we know we're going to have something like this. It may not be like this. These three hydrogens could just be in the same environment. So these six, so these three and these three could be in the same environment, but not right next to each other. But let's just propose this and see if we can fit it in place. And then we know that this carbon will not be bonded to any hydrogens. Then looking at our three hydrogens and a doublet, so we're going to have a carbon. This will most likely, whenever we see these three hydrogens, we're thinking it's going to be the end of a molecule somewhere. And we're going to be bonded to a carbon, and it's going to have one hydrogen bonded to it, and then two other groups. We're not sure about those yet. Oh yeah, I wanted to draw these in red, just to make it clear. So the hydrogens that we're not talking about, the ones on the adjacent, I'm going to draw on in red, okay? And then going on to the next peak, what do we have? We have one hydrogen that looks like one, two, three, four, a quartet, I believe. Should be a quartet. With yeah, that would make sense. Okay, sorry, it's bad quality, guys. Let me just zoom in as much as we can. One, two, three, four. Yes, it is a quartet. Okay, cool. So how many hydrogens was it? We had one hydrogen. We had a quartet. Therefore, n+1 rule. We're gonna have three hydrogens. That says quartet, guys. So let's make that nicer. We have three hydrogens on the adjacent. Where's the shift? Just beneath 4, it appears to be. Let's say 3.9 or 4. Then we check our NMR chemical shifts. 3.94. We can see that this will be a hydrogen onto a carbon, which is then single bonded to an oxygen. Okay? So we have a hydrogen bonded to a carbon, oh my days, which is single bonded to an oxygen. Okay? And we know, so let's draw that on a little bit nicer. But we know, what do we know, guys? We know there are going to be three on the adjacent. So therefore, coming off these two carbons, because we only have one hydrogen in this environment, there must be a total number of three hydrogens around these carbons. So it won't be all six, we're just gonna have to take three of these positions, okay? So let's leave that blank for now, and maybe we'll work it out when building the molecule. So what else do we know? We're told the number of peaks, the relative peak areas, okay? When the spectrum is run without D2O, so the OH or NH peaks will disappear. We know there's not going to be any nitrogens because we have our molecular formula to be C6H12O3. So we know there's not going to be any nitrogens. We're told there's two peaks, one at 11 and one at 3.6. What does this tell us? We're going to have two times this OH, so this hydrogen bonded to the oxygen, these OHs, because we have that D2O. So we know this, but what else do we know? At 11, we have a shift at 11. So we know these can be variable, but the fact that it's 11, what does that tell us? This tells us that it will most likely be a hydrogen bonded to an oxygen, part of a carboxylic acid. So it's a very key thing to remember, guys, okay? So it's also going to be the end of the molecule, which will help us. When we have ends of the molecules, we know this is going to be useful, okay? So we know we're going to have two OHs, and one of them will most likely be part of this carboxylic acid group. So we're going to use that information. So let's start building our molecule. We're going to take things off as we go. We know we have C6H12O3. Let's build the puzzle, or solve the puzzle, sorry. So solving the puzzle, guys, let's do it. So what do we know? We know we're going to have a carboxylic acid group. So you can immediately draw that one now. Now from here, let's kind of think. We know this has to be bonded to a carbon. It can't be bonded to a hydrogen because we need that four bonds on the carbon. So we can just start from there and carry on. Okay? So let's see what we can tick off. We don't currently have hydrogen single bonded to the oxygen. Let's kind of think what we can do. Well, I'm immediately seeing this singlet here. It makes sense. You do have to experiment around, guys. I'm not gonna lie. I'm not gonna lie. If it feels like I've done this first try, it's because I've seen these questions, so I feel like I know where to go. But you can experiment and see how things go. So it makes sense with this carbon. If we want to address these six hydrogens which have a singlet, what we could do is we could bond two carbons to this central carbon and then kind of extend the chain from there. So because we know we're gonna have these two CH3s, we can almost kind of just guess that we'll have the end of the molecules from here. Once again, guys, you may have to experiment a bit, but we can see that this would indeed satisfy our our second thing. So we have these six hydrogens, same environment, with having zero hydrogens on the adjacent carbon. Okay? Let me know if that makes sense, guys. We're kind of just addressing each thing at a time. We could potentially start doing something else, but you would come to this in conclusion at the end. So then what do we know? We then have three hydrogens, doublets. This is going to be the end of the molecule, so we can't worry about that one yet. It's going to be at one end of the molecule, and we can't be the end of the molecule yet because we currently have one, two, three, four, five carbons. We need six carbons. So we know that this carbon will have to be bonded to a carbon, which then has a CH3. We know that has to be the case because we know that CH3 will be at the end of the molecule. But we also know that there's one hydrogen. Guys, give me a thumbs up if this is making sense. But we also know there must be a hydrogen on oh, I'm lagging a bit, making sure we're all good. Okay, we are all good. So we also know there has to be one single hydrogen adjacent to this end of our molecule. So going down here, guys, we know that we're going to have one hydrogen on this carbon. So let's see where we currently are. We've been able to tick off this relative intensity of 3, which has one adjacent hydrogen, as we can see here. We've also been able to tick off these 6 hydrogens in the same environment, only bonded to an alkyl group. So that makes sense because we only have this carbon here. So only bonded to an alkyl group. Okay, with 0 adjacent hydrogens on the carbon. Perfect, because this carbon is not bonded to any hydrogens. We have 2 oxygens. The carboxylic acid group, which could have been from this. Now this is making sense. Which could have been from this, but not yet. Not yet, guys. We still have to address this. Because we have a hydrogen bonded to a carbon, single bonded to an oxygen. That doesn't quite address this just yet. We've addressed one of the OHs because of our D2O. We've addressed one of our OHs because of the D2O, which is perfect. But we still have one more OH. Because remember, we had 2 OHs. We've addressed the one on the carboxylic acid, which has that 11 ppm shift, but we haven't got that 3.6 ppm. We know we already have 6 carbons. This is fine. Let's check the number of hydrogens. 1, 2, 3. 1, 2, 3. That's 6, 7, 8, 9, 10, 11. We need one more hydrogen and one more oxygen. And we know this carbon can't be bonded to any more hydrogens. So let's think about this environment. We now have this one carbon environment. We know that this carbon must be bonded to an oxygen. So there we have it. That solves all of our problems. We have the 2 OHs, the one on the carboxylic acid. We found the molecular, and then we've been able to tick off each box one by one. Does that make sense, guys? Does that make sense? So then we get this. Looks like you guys have named it. Named it already. 1, 2, 3, 4. Yes. First carbon is here. 2, 2, 2. Dimethyl. Yeah, 2, 2. Dimethyl. Well, it actually be 3 hydroxy first because of the alphabetical. So it'd be 3 hydroxy, 2, 2. Dimethyl. Butanoic acid. Because we have that carboxylic acid group. And this satisfies everything. Guys, give me a thumbs up. I think we're going to end the stream here. We're going to do 5 NMR questions at 8 p.m. today, the rest of them in the evening. That would be good practice, and maybe a couple unseen mechanisms. But that is about it. That's about it, guys. Can I run down? So what did we do? We had the masses divided. We had this elemental analysis by mass as percentage. We can use these as the masses divided by the MR, or in this case, We good? Okay, cool. So we divide by carbon 12, hydrogen 1, oxygen 16. Okay? Divide each of these by that, get the smallest possible number, and then divide all of the other numbers by that number. All we're finding is the empirical formula, guys. It's the same. I believe in paper one you have to do this as well. Nothing crazy. So from here, we found the empirical formula. We compared it to the known MR. We saw that we had to times it by 3 to get the MR that we needed. We also knew, because it was run without D2O, we saw 2 additional peaks. So with D2O, because we have that because OH and NH peaks do not appear with D2O because of that proton exchange, we know there's going to be 2 OHs. Why is it 2 OHs and not any NH? Just trying to not lag right now. Okay, because we know our molecular formula have 3 oxygens. But because we had our one shift at 11 ppm, because these peaks are variable, it could just be an OH peak, but we're suspicious that one could be part of a carboxylic acid. From here, we filled out our table, the number of hydrogens with the peaks, which tell us the number of adjacent hydrogens, found the chemical shifts for each one, made certain guesses. So here we had 3 hydrogens. We know it's bonded to an alkyl group with only 1 hydrogen attached to it. Here we had 6, shift 1.3, alkyl group. Then we had the singlet, so we're going to have 0 next to it. So from there, we could guess this group. We kind of made this guess. They could be in different sides of the molecule. How do you know it's an OH but not CHO? Because with the D2O peaks, D2O tell us OH peaks and NH peaks. If it is a H onto a carbon, which is then bonded to oxygen, it will appear here in our NMR. This peak does not get removed when we're in D2O. So yeah, hope everything's good with that, guys. I hope everything is good with that. I will upload a statistics video on my TikTok if you guys want that. It's a predicted topic, but what's the point of predicted topics anymore? I hope I can see you guys in the evening. We're going to be doing more NMR. Oh yeah, just to finish off, we had our 1 hydrogen with that shift with that carbon bonded to the oxygen, and we kind of just experimented around a bit. We knew the ends of our molecule would have to be a CH3, and both of these CH3s were very likely as well, not guaranteed, but very likely. The peak, the peak at 3.9, guys. The peak at 3.9 will be that hydrogen bonded to a carbon to an oxygen. We know it's only going to be a single hydrogen. We know it's going to be a single hydrogen because it tells us the relative intensity, and we know it's going to, because it's a quartet peak, we're going to have 3 adjacents. So we start off with knowing that carboxylic acid will be the end. From here, we can kind of start building our molecule based on what we know. We have those 6 hydrogens in the same environment. This carbon must be bonded to no hydrogens because we had that doublet. Sorry, because we had the singlet. And then from here, we can keep on building. We know we're going to have 6 carbons in total. So keep relating all this information back to each other and keep going. Guys, I'm going to do a geometric series probability distribution question. I'm about to upload it just when we finish. So I'm happy, guys. Hope I see you in the evening. Yeah.